The forest is already beginning to fail, though no single tree announces it. Across the limestone country of southern China, the canopy still stretches over ridges, valleys, and river-cut basins, but its abundance is no longer as dependable as it once was. Fruit ripens unevenly. Dry seasons linger. Familiar feeding grounds become separated by wider spaces of scrub, open woodland, and exposed stone. Somewhere within this changing landscape moves an ape unlike any alive today, a creature so large that later generations will know it almost entirely from the size of its teeth. It does not know that its world is narrowing. For nearly 2 million years, animals of its kind have occupied parts of what is now southern China. They have lived among ancient elephants, rhinoceroses, deer, pigs, monkeys, carnivores, and the distant relatives of modern orangutans. Their range lies in a warm region shaped by monsoon rains, dense vegetation, caves, and the pale cliffs of karst country. In long periods of stability, this is a world capable of sustaining giants. The forest produces fruit, leaves, stems, roots, and other plant foods in immense quantities. The wet seasons renew the land. Trees offer shade, shelter, and predictable resources. A large-bodied ape, adapted to extracting energy from this environment, can survive here for generation after generation. But size is not simply strength. It is a demand placed upon the world. A very large primate must eat heavily and often. It must find enough calories not only during seasons of plenty, but also when fruit becomes scarce, storms fail, or vegetation shifts. It must travel between feeding areas without spending more energy than those areas provide. It must reproduce slowly, as great apes generally do, and replace losses over long spans of time. When conditions remain stable, these constraints may barely be noticed. When the climate begins to swing more sharply between wet and dry, they become dangerous. The animal later named Gigantopithecus Blacki enters the scientific story as the largest known ape. Yet the creature itself remains strangely absent. No complete skeleton has been recovered. There is no skull resting in a museum case, no set of arms and legs that reveals precisely how it stood, climbed, or walked. What survives is more fragmentary and, in some ways, more haunting: thousands of teeth and a small number of massive lower jaws. From these pieces, researchers attempt to reconstruct a body, a diet, an evolutionary relationship, and ultimately an extinction. The familiar image is of a towering ape, perhaps 3 meters tall and weighing several hundred kilograms, but such figures are estimates rather than direct measurements. They are extrapolated from jaws, teeth, and comparisons with living apes. Scholars still debate its exact mass, posture, locomotion, and degree of ground dwelling. Some reconstructions make it look like an enormous orangutan moving below the canopy. Others emphasize that the evidence remains incomplete, and that even close relatives can evolve very different bodies. The safest truth is also the most remarkable. Its jaws and teeth belong to an ape of extraordinary size, one that evolved along the orangutan side of the great ape family rather than along the human line. This distinction matters. Gigantopithecus was not a prehistoric human, not a giant ancestor walking toward humanity, and not a surviving relic hidden in modern forests. Ancient proteins preserved within tooth enamel have linked it to the pongene branch, the evolutionary group that includes orangutans. Its lineage and that of living orangutans likely separated many millions of years ago. By the time Gigantopithecus occupied southern China, it was already the product of a long and independent evolutionary history. Before we go deeper, Take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. The mystery is not simply that such a huge ape once existed. The deeper mystery is how a species that survived repeated environmental changes for such an immense span of time eventually reached a point from which it could not recover. It did not vanish during its earliest appearance, when it was presumably still establishing itself across the region. It persisted through shifting climates, changing animal communities, and repeated glacial cycles. Fossils show that it endured for far longer than our own species has yet existed. Then, during the Middle Pleistocene, its record contracts, its teeth begin to reveal stress, and finally, it disappears. The latest fossil discoveries add detail to this long decline without making it simple. At Yanli Cave, one in Guangxi, researchers recovered additional Gigantopithecus teeth from deposits associated with the transition between the early and middle Pleistocene, broadly around 1.2 to 0.7 million years ago. This interval matters because Earth's climate was changing its rhythm. Glacial cycles were becoming longer and more intense. Regional environments were increasingly shaped by stronger fluctuations, shifting rainfall, and growing seasonality. The new teeth help fill a gap in the animal's history, showing that Gigantopithecus remained present during a period when the stability of its world was beginning to weaken. Yet presence is not the same as security. A species may persist through environmental deterioration for hundreds of thousands of years while becoming steadily more vulnerable. Its population may fragment. Productive habitats may shrink into scattered refuges. Individuals may spend more time searching for food and less time reproducing successfully. None of these changes needs to be sudden. Extinction often appears abrupt only because the fossil record is incomplete. In life, it may unfold as a long series of ordinary difficulties repeated across many generations. What survives in the record suggests that Gigantopithecus was increasingly caught between the requirements of its body and the declining reliability of its habitat. Earlier environments supported diverse forest resources. Later landscapes became more open and seasonal. Fruit remained available, but less consistently. The giant ape appears to have turned more often toward fallback foods, likely including fibrous and less nutritious plant material. Its teeth preserve signs of this adjustment, but adjustment is not always adaptation. Eating poorer food may keep an individual alive through a difficult season while weakening the population over centuries. Nearby, ancient orangutans faced many of the same changes. They also depended on forests and seasonal foods. Yet they appear to have altered their behavior and diet more successfully. Their smaller bodies, greater climbing ability, and broader ecological flexibility may have allowed them to exploit scattered canopy resources, travel differently, and survive periods when preferred foods declined. Gigantopithecus, by contrast, may have been too large to move easily through fragmented treetops and too specialized to transform its feeding strategy quickly enough. This does not mean that size alone doomed it. Large animals can be resilient, and Gigantopithecus had already survived for an extraordinary length of time. Nor does climate change act like a single weapon striking every species in the same way. The same environmental shift can favor one animal, pressure another, and destroy a third. Vulnerability emerges from the meeting point between a changing landscape and the particular habits of the species living within it. There may have been other pressures. Competition for food could have intensified. New predators or diseases may have affected isolated populations. Early humans were present in parts of Asia during the broader period of Gigantopithecus survival, but there is currently no direct evidence that people hunted the giant ape into extinction. No single explanation fully accounts for every detail, and the available evidence does not support turning its disappearance into a simple story of human violence or one sudden catastrophe. Instead, the beginning of the end looks quieter, the rains become less dependable, forests open and close in new patterns, high-quality food becomes harder to predict, the distance between safe habitats increases. A body shaped for abundance must now survive uncertainty. Each generation inherits the same immense frame, the same slow reproductive pace, and the same ecological needs, while the landscape offers less in return. In the fading forests of southern China, the largest ape does not fall in a final dramatic moment. It becomes harder to sustain, harder to replace, and harder to find. Long before the last individual disappears, the conditions that made such an animal possible are already slipping away. The trail leading back to the giant ape does not begin in a cave, a museum, or a formal excavation. It begins in the trade of southern China, among objects sold for purposes that had nothing to do with paleontology. For centuries, fossil bones and teeth had been collected from limestone caves and offered through traditional medicine markets as dragon bones. They were ground into powders, mixed into remedies, and treated as substances of ancient potency. Most buyers never knew which vanished animals had left them behind. A tooth from a rhinoceros, elephant, horse, or primate could pass through many hands before anyone asked what creature it once belonged to. In the early 1930s, the German-Dutch paleontologist Gustav von Koenigswald began examining such material in pharmacies in Hong Kong and southern China. He knew that commercial collections sometimes preserved specimens from sites that had never been scientifically documented. The method was imperfect. Fossils could be separated from their original sediments, mixed with material from distant caves, and stripped of the geological context needed for reliable dating. Yet the markets also contained discoveries that might otherwise have been destroyed or overlooked. Among these fragments, von Koenigswald recognized a molar unlike the tooth of any known living ape. It was enormous, with a broad chewing surface and unusually thick enamel. The crown had been worn through use, but even in that altered state it suggested an animal built to process demanding foods with tremendous force. In 1935 he introduced the name Gigantopithecus Blacki. The genus meant giant ape. The species honoured Davidson Black, the Canadian anatomist whose work on human fossils in China had helped shape the study of Asian prehistory before his death the previous year. The name was dramatic, but the evidence behind it was almost absurdly small. An entire species, potentially the largest ape ever known, had entered science through a single isolated tooth purchased from a shop. That beginning shaped the mystery for decades. Without a known excavation layer, the tooth could not reveal exactly when the animal lived, what other species surrounded it, or what kind of habitat lay outside its cave. Scientists could compare its form with the teeth of orangutans, gorillas, humans, and fossil apes, but nearly every conclusion remained provisional. Some researchers placed Gigantopithecus near the human lineage. Others compared it with extinct Asian apes related to orangutans. The giant tooth became a surface onto which competing ideas about ape evolution could be projected. More specimens gradually appeared. Additional molars and premolars were identified in drugstores and private collections, many believed to have come from caves in southern China. They confirmed that the first tooth was not an abnormal individual. Gigantopithecus truly possessed very large post-canine teeth, exceptionally thick enamel, and chewing surfaces adapted to prolonged force. The front teeth known from later finds were relatively smaller, suggesting that processing food at the back of the mouth was especially important. Still, a collection of teeth is not a body. Early reconstructions varied wildly because scientists had to estimate the animal's proportions from dental size. Some popular images turned it into a towering, upright creature resembling a giant human. Others made it an enlarged gorilla. These reconstructions often reflected assumptions more than evidence. Tooth size does not scale neatly with total body size, and different primates distribute growth differently. The molars made clear that the animal was immense, but they could not reveal a precise height or weight. A major advance came when fossils emerged from documented cave deposits rather than medicine shops. In 1956, researchers working at Yanli Cave in Guangxi recovered a huge lower jaw associated with Gigantopithecus teeth. More mandibular material followed. These jaws were deep, thick, and powerful, with broad tooth rows capable of supporting the molars already known from the markets. The front of the jaw lacked the projecting chin found in modern humans. Its structure belonged unmistakably to a non-human great ape, though one unlike any living species. Liu Cheng and other sites also placed Gigantopithecus within a real Pleistocene animal community. Its remains occurred alongside fossils of elephants, rhinoceroses, deer, pigs, tapirs, bovids, monkeys, carnivores, and ancient orangutans. The giant ape was no mythical survivor from some remote evolutionary age. It lived within relatively recent ecosystems of southern China, overlapping with repeated climate shifts and, during part of its existence, with early members of the human family elsewhere in Asia. Yet cave deposits create puzzles of their own. Gigantopithecus may not have lived inside the caves where its teeth accumulated. Porcupines can collect bones and gnaw them for minerals. Carnivores may carry body parts into dens. Water can wash isolated teeth through cracks and passages. Sediments may be disturbed or redeposited long after an animal dies. Each cave is therefore not a simple graveyard, but a geological archive that must be interpreted carefully. This is one reason teeth dominate the record. Enamel is the hardest tissue produced by a vertebrate body. It survives chemical weathering and physical damage far better than most bone. A large ape dying on the forest floor would leave a skeleton vulnerable to scavengers, acidic soils, roots, flowing water, and tropical decay. Bones could disappear while teeth endured. Once transported into a protected limestone cave, those teeth might survive for hundreds of thousands or even millions of years. Their durability made them excellent messengers, but incomplete ones. A tooth preserves information about growth, diet, wear, chemistry, and evolutionary relationship. It does not directly reveal the length of an arm, the shape of a foot, the flexibility of a shoulder, or the posture of a living animal. The imbalance is extreme: thousands of dental specimens, only a few jaws, and no confirmed complete skull or postcranial skeleton. The medicine shop origin also left a permanent caution. Early specimens without exact provenance remain valuable, but they cannot always be tied securely to a place or layer. Later researchers had to rebuild the story through controlled excavation, stratigraphy, and modern dating. They searched the karst landscapes of Guangxi and neighbouring regions for the caves from which those commercial dragon bones may have come. In effect, science had to return the teeth to their lost world. That effort continues. The 13 dental specimens recovered at Yanli Cave 1 during excavations from late 2023 into early 2024 belong to the same long correction. Unlike the first molar purchased nearly a century earlier, these teeth come from a studied deposit with geological context. Their position near the early Middle Pleistocene transition helps fill a chronological gap between the animal's earlier flourishing and later decline. A fossil that once arrived in science without a landscape is now being understood through landscapes measured layer by layer. There is an irony in this history. Gigantopithecus was first recognized because its teeth were too large to ignore, yet almost everything that made it a living animal remained hidden. Its jaws suggested strength, but not how it moved. Thick enamel suggested demanding foods, but not a single fixed menu. Cave associations suggested a forested region, but not whether it preferred dense canopy, woodland edges, or a shifting combination of habitats. Every answer exposed another absence. What survives in the record suggests that the giant ape was common enough to leave thousands of teeth and rare enough to vanish almost completely as a body. It was preserved not as a skeleton, but as a repeated act of chewing, written across enamel. Its first scientific appearance therefore remains strangely fitting. It did not emerge whole from the ground. It surfaced piece by piece from a drawer of dragon bones, carrying the first hard evidence of a giant whose world had already been lost. Once the teeth are returned to their caves, the mystery becomes more precise rather than less mysterious. The problem is no longer whether Gigantopithecus existed. The evidence for that is overwhelming. The problem is what kind of animal can be reconstructed when nearly the entire species is reduced to enamel and a handful of lower jaws. This imbalance is not unusual in paleontology, but in the case of Gigantopithecus it is unusually severe. Teeth are abundant because they are built to survive. Their enamel resists decay, crushing, chemical attack, and long periods of burial. Bone is far more vulnerable, especially in warm and humid environments where acidic soils, flowing water, roots, microorganisms, and scavengers steadily erase a carcass. A large animal can die beneath a forest canopy and leave almost nothing recognizable after enough seasons have passed. Its teeth may remain long after its ribs, limbs, vertebrae, and skull have disappeared. Southern China is particularly unforgiving to fossil preservation outside protected limestone systems. Heavy rains move sediment through cracks and sinkholes. Karst landscapes contain caves, shafts, underground streams, and chambers that can trap durable objects transported from the surface. Teeth may enter these caves through water, carnivores, porcupines, or the gradual collapse of surrounding deposits. They can survive repeated movement that would shatter or dissolve more fragile bones. The result is a record rich in dental material but poor in the parts needed to reconstruct posture and locomotion. Even the jaws are rare. The known mandibles show that Gigantopithecus possessed a deep and heavily built lower face, but they preserve only one region of the body. They do not reveal the shape of the upper skull, the angle of the neck, or the position of the eyes. They cannot show whether the animal had long arms like an orangutan, a broad chest like a gorilla, or some combination no living ape displays. There are no confirmed femora to indicate how much weight passed through the hind limbs, no hands to show grasping ability, and no feet to reveal how effectively it climbed or walked across the ground. This absence matters because the largest assumptions about Gigantopithecus concern precisely those missing parts. Popular images often depict it standing upright, towering above the forest floor like an enormous human-shaped ape. Others show it as a scaled-up orangutan, heavy-bodied and covered in reddish hair. A different reconstruction may give it the proportions of a gorilla, with massive shoulders and knuckle-walking forelimbs. None of these images is directly supported by a complete skeleton. They are visual hypotheses built from evolutionary relationships, ecological reasoning, and comparison with living primates. The evidence remains incomplete enough that even basic measurements must be treated carefully. Estimates of 3 meters in height or nearly 300 kilograms are often repeated, but they are not measurements taken from a fossil body. They're extrapolations from dental and jaw dimensions, and tooth size does not translate into body mass with perfect consistency. Some primates possess unusually large teeth relative to their bodies, while others have large bodies and less dramatic dentition. Gigantopithecus was certainly enormous by ape standards, but its exact size remains uncertain. The same problem affects behavior. If it was extremely heavy, frequent movement through the upper canopy would have been difficult. Large branches can support substantial weight, but an animal of several hundred kilograms would face limits that smaller orangutans do not. This has encouraged the view that Gigantopithecus spent much of its time on the ground. That inference is reasonable, but it is still an inference, without limb bones, wrists, ankles, or shoulder joints. Researchers cannot determine exactly how terrestrial it was, or whether younger and lighter individuals climbed more often than adults. Its social life is even harder to approach. Teeth can reveal the presence of individuals of different ages, and variation in size may hint at differences between males and females. But the available sample does not provide a clear portrait of group structure. Gigantopithecus may have lived alone, in small family units, or in loose communities that gathered around seasonal foods. Modern orangutans are often used as a comparison because of the evolutionary connection, yet a distant relative living in a different body and environment need not behave in the same way. The temptation to fill these gaps is powerful. A creature of such scale seems to demand a complete image. Museums, documentaries, and illustrations must give it fur, posture, expression, and movement. Science, however, has to remain more restrained. What survives in the record suggests a large pongene ape with extremely robust jaws and teeth adapted to heavy chewing. Beyond that foundation, confidence decreases quickly. Even the cave record can mislead if treated too simply. A fossil tooth found beside the remains of deer, elephants, or carnivores does not prove that all those animals lived at exactly the same moment. Cave deposits can accumulate over long spans. Sediments may be mixed by water, burrowing animals, or collapse. A tooth may be older than the layer in which it is eventually found if it has been reworked from an earlier deposit. This is why modern studies use multiple dating methods and examine the surrounding sediments rather than relying on a single fossil or a single cave. The 2024 extinction study became especially important because it addressed this problem across 22 cave sites rather than building the story around one deposit. Researchers assembled 157 age estimates using 6 dating techniques. They compared caves containing Gigantopithecus with younger caves where the species was absent. They examined pollen, charcoal, sediment chemistry, stable isotopes, dental wear, and trace elements. The goal was not merely to date a tooth, but to reconstruct the changing world around the animal and identify when that world ceased to contain it. The new material from Yanli Cave 1 extends that same effort into an earlier and poorly represented interval. 13 teeth may sound modest, especially for an animal known from thousands of dental specimens, but their value lies in context. They help clarify where Gigantopithecus stood during the transition from the early to the middle Pleistocene, when climate cycles were becoming longer and more intense. Each well-dated cave narrows the uncertainty surrounding the species' persistence and environmental range. Still, fossils do not record life evenly. A cave with many teeth may reflect a nearby population, a long period of accumulation, or an unusually effective process of preservation. A region without fossils may truly have lacked Gigantopithecus, or it may simply lack caves that preserved and exposed its remains. The known distribution across southern China and nearby parts of Southeast Asia is therefore a minimum range, not a complete map. Scholars still debate how widely the animal spread, and whether isolated finds outside the strongest Chinese record belong securely to the same species. There is also a deeper bias in the archive. Teeth tell us most about eating because eating is what wears them down. They preserve scratches, pits, chemical signatures, and structural adaptations connected to diet. This naturally makes Gigantopithecus appear first and foremost as a feeding machine, defined by powerful jaws and the challenge of sustaining a huge body. Its senses, intelligence, emotional life, communication, and social bonds leave almost no direct trace. The animal that emerges from science is therefore shaped by what enamel can remember. Yet that limitation does not make the reconstruction meaningless. A tooth is not merely a hard object. It grows within a living body. Its tissues form at specific stages of development. Its surface contacts food thousands of times. Its chemistry reflects water, vegetation, and the surrounding environment. Stress can interrupt growth. Wear accumulates through repeated behavior. The dental record is narrow, but it is not silent. Gigantopithecus survives as fragments because fragments were what the landscape allowed to endure. The missing skeleton leaves its body uncertain, but the surviving teeth preserve a different kind of biography, one written not in bones of movement, but in the repeated pressures of survival. From those surviving pressures, the outline of the animal begins to emerge, not clearly enough to see it as one might see a living ape moving through the forest, but clearly enough to separate what Gigantopithecus was from what imagination has often made of it. The lower jaws are the first anchor. They are exceptionally deep and thick, built to withstand powerful forces generated during chewing. The tooth rows are broad, and the molars are enormous, with crowns designed for prolonged crushing and grinding. Thick enamel covers the chewing surfaces, protecting them against repeated abrasion and allowing the teeth to remain functional despite heavy wear. This was not a delicate feeder taking small, soft items with minimal effort. Whatever its preferred foods may have been, its mouth was capable of processing material that demanded strength, persistence, and a substantial investment in dental structure. Yet large teeth do not automatically mean a diet of hard objects. Thick enamel can protect against grit, tough plant tissues, accidental contact with seeds, or the repeated use of fallback foods during lean seasons. The rounded cusps and broad surfaces of the molars fit a plant-heavy diet, but they do not point to one exclusive food. Earlier researchers sometimes imagined Gigantopithecus as a bamboo specialist, partly because of comparisons with the giant panda, and partly because bamboo was common in some reconstructions of its habitat. Later evidence has made that picture too narrow. Dental wear and chemical signatures suggest a varied terrestrial plant diet that could include fruit, leaves, stems, roots, bark, and other fibrous resources. Its feeding strategy was specialized, but not necessarily around a single plant. The jaw itself may reveal something about the face. A mandible this robust would have supported strong chewing muscles and a large lower facial region. The skull was probably correspondingly substantial, though its precise shape remains unknown. Reconstructions often give Gigantopithecus a broad, heavy face with pronounced muscle attachments and a relatively projecting muzzle. This is plausible when compared with other great apes, but without a cranium, the height of the face shape of the brow, size of the brain case, and position of the nasal opening remain matters of inference. The teeth also show that this animal did not belong on the human side of the great ape family. For much of the 20th century, some researchers entertained the possibility that Gigantopithecus was connected to human ancestry. Its enormous molars and thick enamel appeared, at first glance, to echo features seen in certain fossil hominins. In an era when the Asian fossil record was poorly understood, the idea of a giant human relative did not seem as implausible as it does now. That interpretation weakened as comparative anatomy improved. The structure of the jaws and teeth fit more comfortably among the pongines, the branch of great apes that includes living orangutans and their extinct relatives. Even so, morphology alone could not settle every dispute. Convergent evolution can cause unrelated species to develop similar features when they face similar ecological demands. Thick enamel, for example, can evolve more than once in primates that process abrasive or mechanically difficult foods. The decisive advance came from a place where ancient DNA could not easily survive. Warm, humid environments are destructive to genetic material, and the age of Gigantopithecus fossils places them far beyond the reliable recovery of DNA in most tropical settings. Tooth enamel, however, can preserve proteins for much longer. In 2019, researchers extracted ancient enamel proteins from a molar, roughly 1.9 million years old. Those molecular traces provided the first direct biochemical evidence of the giant ape's evolutionary position. The result placed Gigantopithecus within the pongine lineage and showed that its closest living relatives are orangutans, not humans, gorillas, or chimpanzees. The line leading to Gigantopithecus had separated from the lineage leading to modern orangutans many millions of years earlier, probably during the Miocene. By the Pleistocene, the two were distant cousins rather than near equivalents. Still, the protein evidence transformed the animal from a vaguely placed giant ape into a recognizable branch of the orangutan side of the family tree. This relationship gives researchers a useful comparison, but also a dangerous temptation. It is easy to take an orangutan, enlarge the body, place it on the ground, and declare the reconstruction complete. Evolution does not work so neatly. Distant relatives can retain inherited traits while developing entirely different proportions, behaviors, and ecological strategies. Gigantopithecus may have shared aspects of facial anatomy, dental development, or metabolism with other pongines, but millions of years of separation allowed ample time for dramatic divergence. Its body mass remains among the most debated features. Popular estimates often place the largest individuals between roughly 200 and 300 kilograms, with some reconstructions extending even higher. These numbers would make Gigantopithecus heavier than most wild gorillas and vastly larger than living orangutans. Yet body size inferred from jaws and teeth carries wide uncertainty. The relationship between molar area and body mass differs among species, especially when one lineage evolves unusually enlarged chewing structures. The famous image of a 3-meter-tall ape is even more uncertain because height depends on posture. A quadrupedal ape does not carry its body in the same way as a human. Standing height, shoulder height, and total body length can produce very different impressions. Gigantopithecus may indeed have been exceptionally tall when rearing upright, but there is no evidence that it habitually walked on 2 legs. Its evolutionary relationship and probable body mass make quadrupedal movement far more likely, perhaps with occasional upright postures for feeding, display, or reaching, as seen in living great apes. How it moved on all 4s remains unknown. It might have used a form of fist walking, knuckle-supported movement, or another terrestrial pattern with no exact modern equivalent. Orangutans move through trees using flexible joints and multiple hand and foot positions, while gorillas are more committed to knuckle walking on the ground. Without wrist, hand, ankle, or limb fossils, assigning either pattern to Gigantopithecus would go beyond the evidence. Its immense size probably reduced its ability to move through thin branches, particularly as a full-grown adult. A younger animal may have climbed more readily, while large males or females remained mainly below. Sexual differences could also have been considerable. Living orangutans show strong size differences between adult males and females, and other great apes display their own forms of sexual dimorphism. The Gigantopithecus teeth vary in size, but the fossil sample does not yet allow researchers to identify sex confidently or determine how extreme those differences were. Colour and coat are almost entirely unknown. The common reddish-brown reconstruction follows its relationship with orangutans, but fur pigmentation does not fossilize in teeth. Dark brown, black, reddish, or mixed coloration are all possible. Hair length would have depended on temperature, humidity, parasites, and behavior. Southern China experienced major climatic fluctuations during the long existence of the species, so its coat may not even have remained identical across its entire range and history. The size of its brain is equally obscure. No brain case survives. It was a great ape and therefore likely possessed complex cognition, memory, social awareness, and flexible learning, but there is no basis for assigning it human-like intelligence or dismissing it as a slow, unintelligent brute. Large body size does not directly determine cognitive ability. Its survival across changing Pleistocene environments for well over 1 million years suggests a species capable of responding to variation, even if those responses eventually became insufficient. What emerges is not a monster and not a missing human ancestor. It is a highly distinctive pongene, shaped by a long evolutionary experiment in size, feeding power, and life within the forests and woodlands of southern Asia. The jaws reveal strength. The enamel reveals endurance. Ancient proteins reveal kinship. The missing skeleton preserves uncertainty. That uncertainty should not diminish the animal. It should sharpen the image. Gigantopithecus was real enough to leave teeth larger than any living apes, yet distant enough that its face, gait, coat, and expression remain beyond recovery. Science can place it on the tree of life and estimate the demands of its body, but the complete creature still stands just outside the light, reconstructed from the hardest parts it left behind. To understand how such an animal could exist at all, the body must be placed back inside the world that supported it. Southern China during the early Pleistocene is not a single unchanging forest stretching across 2 million years. It is a shifting mosaic shaped by monsoon rains, river systems, limestone ridges, seasonal wetlands, dense woodland, open patches, and repeated climatic pulses. Yet for long intervals, the region remains warm, productive, and rich enough to sustain one of the most extraordinary communities of large mammals known from prehistoric Asia. Across what is now Guangxi and neighbouring areas, pale limestone rises from the landscape in steep towers and broken ridges. Rainwater dissolves the rock over immense spans of time, carving sinkholes, caves, shafts, and underground channels. Rivers thread through lowlands between the karst formations. Forests gather in sheltered valleys and climb across humid slopes. In wetter phases, the canopy can be thick and layered, producing fruit at different heights and seasons. In drier phases, woodland opens, grasses spread into clearings, and some forest plants retreat toward river margins and protected basins. Gigantopithecus lives within this complexity rather than in a simple tropical jungle. Its environment changes from place to place and from century to century. Some areas offer dense evergreen forest, others contain mixed woodland with more pronounced seasonal leaf loss. Bamboo, palms, figs, broadleaf trees, shrubs, climbing plants, and ground vegetation contribute to a broad range of possible foods. The precise composition varies, and scholars still debate which plants were most important to the giant ape. But the region clearly provides enough plant biomass to support large herbivores and omnivores in remarkable numbers. The animal community around it is crowded. Ancient elephants move through river valleys and forest margins, opening paths and breaking vegetation. Rhinoceroses browse among shrubs and low trees. Tapirs feed near water and within dense cover. Deer and bovids occupy woodland edges and more open ground. Wild pigs disturb the soil while searching for roots and fallen foods. Monkeys move through the canopy, while ancient orangutans exploit fruits and leaves above. Carnivores, including large cats, hyenas, and other predators, follow the herds and patrol the same corridors between water and shelter. This is not a peaceful Eden. Competition exists at every level. Fruit eaten by one species is unavailable to another. Dry seasons force animals toward the same rivers and remaining patches of vegetation. Predators target the vulnerable. Disease spreads through dense populations. Storms, floods, and landslides alter familiar routes. Yet abundance allows many species to coexist because they divide the landscape and its resources in subtle ways. One feeds high in the canopy, another on the ground. One specializes in leaves, another in fruit, roots, bark, or grasses. Size, timing, digestive ability, and movement all determine who can use what. Gigantopithecus occupies one of the largest body positions in this system. Its immense jaws and molars allow it to process plant foods that smaller apes might avoid or use only during scarcity. Fallen fruit may have been important, especially in seasons when the forest floor was littered with high-energy food. Fibrous stems, tough leaves, underground storage organs, bark, and other mechanically demanding plants could supplement the diet when preferred items declined. Thick enamel would help the teeth endure repeated chewing, accidental grit, and the abrasion that comes from feeding close to the ground. The forest floor offers opportunities that the canopy does not. Large fruits fall there. Roots and shoots can be reached without climbing. Streams expose soft vegetation along their banks. Seasonal flooding deposits fresh sediment and encourages new growth. A huge ape moving mainly below the trees could exploit these resources while avoiding the structural limits of thin branches. It may have travelled along established animal paths, through openings created by elephants and other megafauna, or beside rivers where movement was easier. Still, the same ground-level life brings risks. A large body is difficult to conceal. Young or weakened individuals may have been vulnerable to large predators. Open patches expose animals to heat and make travel between forest refuges more costly. Karst terrain can be physically demanding, with steep slopes, broken rock, sinkholes, and narrow passages. The landscape is productive, but not gentle. Water would have shaped daily movement. In humid periods, streams and pools are widespread. In seasonal phases, reliable water sources become centers of activity. Gigantopithecus likely returned repeatedly to rivers, springs, or wet depressions, though no trackways preserve those journeys. Its teeth and cave associations place it within these landscapes, but they do not record a route from one feeding area to another. What survives in the record suggests an animal tied closely to environments where water, vegetation, and shelter remained sufficiently dependable. The monsoon system is crucial. Seasonal winds bring moisture from warm seas into southern China, feeding forests and rivers. But monsoon strength changes with global climate, ocean temperatures, ice volume, and shifts in Earth's orbit. During some periods, summer rains are strong and ecosystems flourish. During others, dry seasons lengthen and rainfall becomes less predictable. These fluctuations are not yet fatal to Gigantopithecus during the earlier part of its history. This species persists through them, suggesting that its ecological strategy works well when changes remain within a certain range. The newly reported fossils from Yanli Cave fall within a particularly important interval, roughly the transition between the early and middle Pleistocene. Around this broad span, climate cycles begin changing in pace and intensity. Glacial periods become longer, and environmental swings grow more pronounced. Southern China never turns into the ice-covered landscape seen farther north, but the global reorganization affects temperature, rainfall, vegetation, and the timing of food production. The forests continue, though not always in the same form or with the same reliability. For a long-lived species, this transition would not appear as one sudden crisis. Generations would experience different versions of the same region. One period might bring humid forests and abundant fruit. Another might favor more open woodland, tougher vegetation, and longer intervals between productive seasons. Populations could shift locally, following suitable habitat into valleys, river corridors, and protected karst basins. The 13 teeth from Yanli Cave help show that Gigantopithecus remained part of this world during that transformation, surviving conditions that were already becoming less stable. Caves preserve the animal communities of these landscapes unevenly. A deposit may contain teeth from species that live nearby over thousands of years. Floodwater may carry remains into underground chambers. Porcupines may collect bones. Predators may drag prey into sheltered spaces. The caves are therefore not snapshots in the modern sense, but layered accumulations of environmental history. Even so, when similar faunal associations appear across multiple sites, they reveal a regional pattern. Gigantopithecus belongs to warm temperate and subtropical ecosystems rich in forest animals, especially during the earlier and middle phases of its existence. This broader world also helps explain its extraordinary size. Large bodies are often favored where food is abundant. Competition can be met through strength or digestive capacity, and adult survival is high enough to offset slow reproduction. A giant ape able to process large quantities of vegetation may have occupied a niche that no living primate fills today. Its size could deter many predators, improve access to ground-level resources, and allow it to survive short periods of poor-quality food by carrying greater energy reserves. But every advantage is conditional. A large body works only while the environment can continue paying its energetic cost. Productive forests make Gigantopithecus possible. Seasonal but predictable landscapes allow it to persist. River valleys and wooded basins connect feeding grounds. Once those conditions begin to fragment, the same scale that once made the ape formidable becomes increasingly difficult to support. For now, however, the giant remains at home. It moves beneath trees that have fed its lineage for countless generations. Around it, elephants reshape the undergrowth, monkeys disturb the canopy, and ancient orangutans travel through branches overhead. The air carries moisture from the monsoon. Rivers cut deeper into limestone country. Fruit falls, vegetation renews itself, and the forest still produces enough to sustain an animal built on an almost unimaginable scale. An animal of extraordinary size lives under a simple law the landscape must keep feeding it. Strength, heavy jaws, thick enamel, and a large digestive system are advantages only when enough energy moves through the body each day. For Gigantopithecus, feeding is not one part of life among many. It is the central problem around which movement, habitat, reproduction, and survival are organized. The largest living apes already devote much of their time to finding and processing food. Gigantopithecus almost certainly required more. Its exact body mass remains uncertain, but even conservative estimates imply an enormous daily demand. A large primate can carry greater reserves than a smaller one, and its slower metabolism per unit of body weight may offer some efficiency. Yet the total amount of food still has to be substantial. The animal must locate enough edible material, chew it effectively, digest what nutrients it contains, and do so without spending excessive energy in the search. Its teeth provide the clearest clues. The molars are broad, low-cusped, and protected by remarkably thick enamel. Their surfaces are built for crushing and grinding rather than slicing flesh. The heavy lower jaw resists repeated mechanical stress. Together, these features point toward a diet dominated by plants, but they do not identify one narrow menu. Earlier images often presented Gigantopithecus as a bamboo-eating giant, almost an ape counterpart to the panda. Bamboo may well have formed part of its diet in some places or seasons, but the available evidence does not support describing it as an exclusive bamboo specialist. Instead, the teeth suggest flexibility within a plant-based feeding system. Fruit was probably valuable whenever available because it supplies sugars and other easily accessible calories. Figs and similar forest fruits can support many primates, while larger fallen fruits may have been especially accessible to a heavy ground-dwelling ape. Leaves, young shoots, stems, roots, bark, and underground plant parts could broaden the menu. Some foods may have been soft and nutrient-rich. Others required long periods of chewing and offered much less energy in return. This difference between preferred foods and fallback foods becomes crucial. Many primates eat one set of foods during times of abundance, and another when conditions deteriorate. Fruit may dominate during productive seasons, while leaves, bark, or fibrous stems keep the animal alive during shortages. The fallback diet can determine whether a species survives environmental stress. It does not need to be pleasant or highly nutritious. It only needs to remain available and digestible when better options disappear. Gigantopithecus appears well equipped to process difficult fallback foods. Thick enamel protects against wear. Massive molars grind fibrous material. Strong jaws generate sustained force. Yet the ability to chew a food does not mean that the food can fully support the body. Tough vegetation may fill the stomach while providing too little usable energy. An individual can survive this way for a time, but prolonged dependence on poor quality resources can affect condition, fertility, and resistance to disease. Its feeding height may also have mattered. A very large adult probably found much of its food on or near the ground, where fallen fruit, roots, shoots, and low vegetation were available. It may have pulled branches downward, stripped bark, broken stems, or dug into softer soils for underground resources, though no hand bones or direct traces confirm these behaviors. Comparisons with living apes make such possibilities reasonable, but the evidence remains incomplete. Ground feeding offers efficiency when resources are concentrated. A productive fruiting tree can scatter large amounts of food over a small area. Riverbanks and disturbed ground may produce dense patches of young vegetation. Elephant trails can expose roots and open access through undergrowth. In favorable seasons, a giant ape might feed for long periods without traveling far. Scarcity reverses that advantage. When fruiting trees are separated, the ape must cross greater distances. When dry seasons intensify, streams shrink and plant growth slows. When forests fragment, high-quality food may remain in scattered canopy patches that smaller, more agile primates can reach, but an enormous animal cannot use easily. The problem is not simply whether food exists somewhere in the landscape. It is whether enough food exists within an economical distance and in a form the animal can obtain. Dentalware helps reveal how the answer changed over time. Microscopic scratches and pits form as food passes repeatedly across enamel. Different textures can leave different patterns, though these signals must be interpreted carefully because grit, dust, and seasonal variation also affect wear. Earlier Gigantopithecus populations show evidence consistent with access to a broader and more stable range of forest foods. Later specimens suggest increasing reliance on tougher, more fibrous material as environments became more seasonal. Stable isotopes add another layer. Chemical signatures locked into teeth reflect the plants and habitats contributing to an animal's diet. These records indicate that Gigantopithecus remained closely connected to forested environments, rather than shifting successfully into open grasslands. This ecological attachment may once have been a strength. Forests supplied the foods its body and teeth were adapted to exploit. As forest structure changed, however, that attachment limited the alternatives available. Trace elements and growth disruptions within teeth may preserve evidence of physiological stress. Teeth form over time, recording episodes when nutritional health is disturbed. Later populations appear to have experienced greater stress than earlier ones. The signal is not a diary of individual hunger, and no single tooth can explain an extinction. Across many specimens and sites, however, the pattern suggests that feeding became more difficult as the species approached its final phase. A surprising feature of this story is that the mouth of Gigantopithecus was powerful enough to handle increasingly difficult foods, yet this very capacity may have concealed the decline. A population can persist while shifting toward lower quality resources. Adults continue feeding. Teeth continue wearing down. Individuals remain present in the fossil record. Beneath that apparent survival, reproductive success may fall and mortality may rise. Extinction does not require every animal to starve at once. It requires losses to exceed replacements for long enough. Slow reproduction would make recovery especially difficult. Like other great apes, Gigantopithecus probably matured gradually and produced young at long intervals. This cannot be proven without a complete life history record, but its evolutionary position makes rapid reproduction unlikely. If females entered breeding condition less often during nutritional stress, or if adults spent more energy traveling between feeding patches, population growth could weaken over many generations. Seasonal shortages would also affect individuals unevenly. Large adults might endure temporary scarcity by drawing on body reserves, while younger or older animals may have been less resilient. Direct evidence for these differences does not survive, and the record cannot safely reconstruct specific family scenes. What it does suggest is a species whose demographic stability depended on the regular return of productive seasons. Ancient orangutans faced the same changing forests but approached the feeding problem differently. Their smaller bodies required fewer total calories. Their climbing ability opened access to foods remaining in the canopy. A broader behavioral repertoire may have allowed them to switch feeding locations and exploit resources scattered across vertical layers of the forest. Gigantopithecus could process tougher foods, but Pongo may have been better able to reach a wider selection. This contrast reveals the trap hidden inside specialization. The giant ape's jaws are not evidence of weakness. They are evidence of a successful adaptation that worked for an immense span of time. A powerful chewing system allowed it to use foods unavailable or unattractive to other primates. Large size likely offered protection and efficiency. The problem emerged when environmental change altered the balance between the calories required and the calories obtainable. No single plant disappeared and caused the extinction. No one failed fruiting season ended the lineage. The pressure accumulated through repetition, fewer dependable fruits, longer intervals of poor food, greater travel between productive patches, and increasing dependence on fibrous substitutes. Each change was survivable on its own. Together, they steadily raised the cost of being enormous. The same teeth that once opened a rich ecological opportunity eventually record the narrowing of that opportunity. Their enamel survives because it was built to resist damage. Their wear shows that the animal continued chewing through difficult times. But even the strongest mouth cannot extract unlimited energy from a landscape that is offering less. A landscape that offers less food does more than change what an animal eats. It changes how far that animal must travel, how long it can remain in one place, how often it encounters others, and how much energy remains for everything beyond feeding. For Gigantopithecus, daily life probably unfolded as a constant negotiation between movement and cost. Its size would have shaped every journey. A very large ape can cross ground efficiently over short distances, but long travel becomes expensive when the body must be supplied continuously. Steep limestone slopes, broken rock, dense undergrowth, rivers, and seasonal mud would add further difficulty. The karst country of southern China is visually dramatic, but for a heavy terrestrial animal, it is also a terrain of barriers. Valleys may offer easy routes, while ridges and cliffs divide one productive basin from another. When forests remain continuous, these obstacles can be bypassed beneath the canopy. When habitats fragment, the gaps become more serious. Gigantopithecus was probably more ground-oriented than living orangutans, especially as a mature adult, though this remains one of the most persistent uncertainties in its reconstruction. Its body size alone makes frequent movement through smaller branches unlikely. A giant adult could perhaps climb broad trunks or use massive lower limbs of trees, but the upper canopy would impose structural limits. Younger individuals, being lighter, may have climbed more often. No hand, foot, shoulder, or ankle fossils survive to confirm these possibilities, so any description of its locomotion must remain cautious. On the ground, it may have moved on all fours using a pattern unlike that of any living ape. Its distant relationship to orangutans suggests flexible joints somewhere in its ancestry, but millions of years of adaptation to greater size could have transformed the limbs substantially. It may have supported weight on the knuckles, on the sides of the hands, or through another posture. Habitual upright walking is unsupported by the fossil record, despite its frequent appearance in popular reconstructions. Like living great apes, it could probably rear onto two legs briefly to reach vegetation, survey its surroundings, or display. But that is very different from moving bipedally across the landscape. Most days likely began and ended near dependable resources: water, fruiting trees, dense feeding patches, and secure resting areas would organize movement. A large animal may not need to travel constantly when food is abundant. It can remain near a productive location, feeding slowly and processing large quantities. During leaner periods, however, the daily range may expand. Each additional kilometre consumes energy that must eventually be replaced, creating a dangerous cycle when food patches are scattered. The ape's route through the forest may have followed memory as much as immediate scent or sight. Great apes possess strong spatial awareness and can remember the locations and seasonal timing of foods. Gigantopithecus probably did not wander randomly. It may have returned to known trees, riverbanks, mineral sources, and sheltered valleys according to patterns learned over years. Such knowledge would be especially valuable in a seasonal environment where a resource might be abundant for only a short period. Intelligence of this kind leaves no direct mark on enamel, but it is a reasonable inference from its position among the great apes. There is no evidence that Gigantopithecus made stone tools, controlled fire, or developed human-like technology. There is equally little reason to imagine it as an unthinking brute. Its lineage persisted through repeated climatic changes for more than 1 million years. Survival on that scale requires learning, memory, communication, and behavioral adjustment. Even if those abilities never produced artifacts that archaeologists can recover, its social organization is harder to infer. Living great apes show strikingly different patterns. Gorillas often live in stable groups. Chimpanzees form flexible communities with shifting parties. Orangutans are more dispersed, though their social lives are more complex than the old image of complete solitude suggests. Gigantopithecus could have followed one of these broad patterns, or evolved something distinct. A huge body and reliance on dispersed plant foods may have favoured relatively small social units. Large groups can deplete a feeding patch quickly, especially when each member requires substantial calories. Solitary adults or loose associations would reduce direct competition. On the other hand, social bonds can improve protection, mating opportunities, knowledge transfer, and access to young. The fossil record offers no nesting sites, trackways, or death assemblages that reveal how many individuals travelled together. Variation in tooth size may indicate sexual dimorphism, perhaps with males larger than females, as in orangutans and gorillas. If this was the case, adult males and females may have used the landscape differently. Large males might range widely between the territories or home areas of several females, or dominant individuals might control access to productive sites. These possibilities are plausible, but remain speculative because individual sex cannot be assigned securely from most isolated teeth. Reproduction would almost certainly have been slow. Great apes mature over many years, invest heavily in each offspring, and reproduce at long intervals. Gigantopithecus likely followed the same general pattern, though exact gestation, age at maturity, and spacing between births are unknown. A long developmental period would allow young animals to learn the geography of the forest and the use of difficult foods, but it would also make the species vulnerable to sustained population decline. The care of young probably involved close and prolonged protection, as it does in all living great apes. Younger individuals may have remained near an adult caregiver while learning feeding routes and safe movement through the landscape, because the evidence does not preserve direct scenes of family life. The reconstruction must remain general. What matters demographically is that each successful offspring represented years of biological investment. A population losing adults faster than young could mature would recover only slowly. Resting behavior also remains hidden. Living orangutans build nests in trees, while gorillas may sleep on the ground or in low vegetation. A very heavy Gigantopithecus may have constructed ground nests from branches and leaves, used sheltered hollows, or selected broad, stable tree platforms. Caves are unlikely to have been its ordinary home simply because its teeth are found there. Most cave deposits accumulated through transport or animal activity after death. There is no convincing evidence of repeated occupation by living Gigantopithecus. The forest canopy still mattered even if the ape remained mainly below it. Overhead branches regulated shade, moisture, fruit production, and the structure of undergrowth. The canopy was not merely a roof but the engine of the ecosystem. When it thinned, temperatures near the ground rose, soils dried more quickly, and familiar plant communities changed. A terrestrial ape could therefore be deeply dependent on trees without spending most of its time in them. Encounters with predators may have been uncommon for healthy adults. Exceptional size alone would discourage many attackers. Large cats or packs of carnivores could still threaten isolated, injured, or weakened animals, but no fossil evidence shows regular predation. Gigantopithecus teeth found in caves sometimes bear damage, yet such marks may result from porcupine gnawing, transport, or post-depositional processes rather than attacks on living apes. Interactions with other herbivores may have been more frequent and more important. Pigs, deer, tapirs, elephants, monkeys, and orangutans all drew from overlapping plant resources. Competition did not require direct confrontation. A herd consuming fallen fruit before a giant ape arrived could matter more than any physical contest. Elephants might simultaneously reduce some food sources and create others by opening vegetation and exposing new growth. Ecological relationships rarely divide neatly into ally and rival. Early humans had another uncertain presence. Members of the human lineage occupied parts of Asia during the long span of Gigantopithecus existence, but there is no secure evidence of direct encounters, hunting, or competition severe enough to explain the giant ape's disappearance. Their ranges may sometimes have overlapped, yet the caves have not produced a clear scene linking stone tools. Butchered Gigantopithecus remains, and human activity. Popular images of prehistoric hunters confronting the giant ape go far beyond what the evidence supports. Most of its life was probably less dramatic. It moved between feeding grounds, rested, watched, remembered, chewed, and followed the changing productivity of the forest. Rain altered its routes, dry months lengthened them. Familiar trees failed in some years and flourished in others. The animal responded through behavior because behavior is the first line of adaptation. But behavior has limits. Memory cannot restore a forest that no longer fruits reliably. Strength cannot shorten the distance between isolated habitats. A slow breeding population cannot quickly replace losses caused by repeated nutritional stress. The giant ape may have adjusted its routes and diet many times, yet each adjustment took place inside a body whose basic requirements had been shaped during a more generous age. Its daily life, therefore, contains the first signs of the larger extinction pattern. The crisis is not visible as a single catastrophe. It appears in longer walks, poorer meals, fewer dependable refuges, and a growing mismatch between the geography remembered by the animal and the landscape that now surrounds it. The body of Gigantopithecus is largely gone, but its teeth have preserved a record far richer than their size alone suggests. Each molar began forming inside a living jaw. Layer by layer, enamel and dentine captured chemical traces from food, water, growth, stress, and the surrounding environment. Once the tooth erupted, its surface began recording a second history through scratches, pits, fractures, and polish. The animal vanished, yet these small mineral archives survived long enough for modern laboratories to read them. A fossil tooth does not tell its story in a single way. Its shape reflects inherited anatomy and long-term adaptation. Its wear reflects repeated contact with food and particles in the environment. Its chemistry reflects the plants entering the food chain and the water moving through the landscape. Trace elements can reveal changes during growth, while microscopic defects may indicate periods when the body experienced nutritional or physiological strain. None of these signals is perfectly direct, but when many teeth from different sites and ages are compared, patterns begin to emerge. The broad crowns and thick enamel show that Gigantopithecus was built for sustained chewing. Enamel thickness is especially important because it protects the tooth against abrasion and prevents rapid damage when foods contain grit, tough fibers, hard outer layers, or resistant plant tissues. A thinner enamel surface might wear through too quickly under those conditions. Gigantopithecus instead carried a dental system capable of enduring years of heavy use. Yet thick enamel is not a simple label for one diet. It does not prove that the ape ate only nuts, seeds, or bamboo. Hard object feeding can produce certain forms of damage, but tough foods and abrasive foods are not the same. A leaf can be mechanically difficult without being hard. Soil-covered roots can introduce more abrasion than soft fruit. Dust and mineral particles carried by dry season winds can alter wear, even when the food itself is not especially resistant. Researchers therefore avoid assigning a menu from enamel thickness alone. Microwear provides a more immediate view of feeding. Under magnification, the chewing surfaces of teeth display patterns created during the final days or weeks before death. Fine scratches may be associated with shearing fibrous material or with abrasive particles. Pits can form when harder objects are crushed. The density, depth, and orientation of these marks help researchers compare one population with another. Earlier Gigantopithecus teeth generally suggest access to a broad range of forest foods and relatively stable feeding conditions. Later teeth show patterns consistent with increasing reliance on tougher and more fibrous fallback resources. This does not mean that every late individual ate the same poor diet or that fruit vanished completely. Microwear captures only a short interval in one animal's life, across multiple specimens. However, the shift supports the larger environmental evidence that preferred foods were becoming less predictable. Stable isotope analysis looks deeper into the life of the tooth. Plants use different photosynthetic pathways, and the isotopic signatures produced by those pathways can pass into animal tissues. Forest plants growing beneath a closed canopy also create different chemical conditions from vegetation in more open settings. By examining carbon and oxygen isotopes, researchers can estimate whether an animal fed mainly within dense forest, open woodland, grassland, or some mixture of habitats. Gigantopithecus remained strongly associated with forest resources. Even as the regional landscape became more open and seasonal, it did not appear to make a successful ecological transition into grass-dominated environments. This is a critical point. The problem was not simply that the climate changed. Many animals survive climate change by shifting their range, altering their diet, or exploiting new habitats. Gigantopithecus seems to have remained tied to the shrinking and restructuring forest system on which its feeding adaptations depended. Its ancient orangutan contemporary, Pongo weidenreichi, left a different pattern. The orangutan lineage appears to have maintained a broader dietary response during the same environmental instability. It could use foods from different vertical layers of the forest and may have adjusted more effectively as fruiting patterns changed. The comparison is not one between an adaptable species and a completely inflexible one. Gigantopithecus also changed its diet. The difference is that the orangutan's adjustments appear to have remained sustainable, while the giant apes increasingly depended on lower quality resources. Trace element analysis offers clues about how these changes affected the body. As teeth form, elements from diet and metabolism are incorporated into their tissues. Variations can indicate altered food sources, changing environmental exposure, or periods of biological stress. Researchers have used these microscopic chemical patterns to compare Gigantopithecus populations from earlier and later phases of its existence. The later teeth show greater instability. Their chemical profile suggests that individuals experience more variable nutrition and increased stress as the environment became less dependable. These signals must be interpreted cautiously. Illness, pregnancy, local habitat differences, and seasonal shortages can all affect tooth chemistry. No single line proves extinction. Combined with dating, pollen, sediment, and microwear evidence. However, the pattern becomes difficult to dismiss. Growth defects provide another form of evidence. Enamel forms incrementally and cannot repair itself once development is complete. If a young animal experiences severe nutritional stress or illness while a tooth is forming, the disruption may leave a visible line or structural defect. Such features do not identify the exact cause, but they reveal moments when normal growth was interrupted. In a stable population, some individuals will always experience hardship. The important question is whether stress becomes more frequent, more widespread, or more intense through time. What survives in the Gigantopithecus record suggests that later populations were living closer to their ecological limits. The teeth continue to grow, but they carry more signs that the body had struggled while producing them. The caves surrounding those teeth preserve the wider environmental story. Pollen grains identify changing plant communities. Charcoal records shifts in fire activity, which may reflect drier conditions, more open vegetation, or natural burning patterns. Sediment layers reveal episodes of water flow, erosion, cave formation, and landscape instability. Animal fossils show which species remained present as habitats changed. The 2024 study brought these different archives together across 22 caves in Guangxi. Rather than relying on one method, researchers used 6 dating techniques to establish 157 age estimates. This was essential because cave deposits can be disturbed, mixed, or redeposited. A tooth alone may not provide a reliable age. The sediments above, below, and around it must be tested, and the results must agree with the broader stratigraphy. Methods including luminescence dating, uranium series analysis, and other chronological techniques allowed the team to define a far narrower extinction window than earlier estimates. Gigantopithecus appears to disappear between roughly 295,000 and 215,000 years ago. This species did not simply fade from an undated cave record. Its final presence could now be placed against a sequence of environmental deterioration and dietary stress. The fossils from Yanli Cave 1 add another point to that sequence, much earlier in the story. Their position near the early Middle Pleistocene transition, broadly between 1.2 and 0.7 million years ago, helps reveal the ape during a period when climate variability was intensifying. These teeth do not record the final extinction crisis, but they help bridge the long interval between early success and late vulnerability. They show that the lineage endured major climatic reorganization before its final decline. This endurance matters because it prevents an overly simple explanation. Gigantopithecus did not disappear at the first sign of cooler temperatures or increased seasonality. It survived repeated cycles, its populations adjusted, persisted, and perhaps shifted across the landscape for hundreds of thousands of years. The final extinction occurred only when environmental instability crossed a threshold that its biology and behavior could no longer compensate for. The most revealing evidence is therefore not a single dramatic wound or catastrophic layer. It is convergence of subtle signals: changing pollen, altered sediment, greater seasonality, broader microwear variation, increased use of fallback foods, and chemical signs of stress. Each clue is modest. Together, they describe an ecological system becoming less reliable around a species with unusually high demands. A tooth seems like a small remnant from which to reconstruct such a vast history. Yet enamel preserves what flesh and bone could not. It records the forest entering the mouth, the climate entering the forest, and stress entering the growing body. Gigantopithecus left no written account of its changing world. It left the world written into its teeth. The change recorded in those teeth begins long before the species disappears. It develops across hundreds of thousands of years as the forests of southern China become less predictable, more seasonal, and increasingly divided into habitats that do not always provide the same foods at the same time. For an animal adapted to abundance, the danger is not that the forest vanishes overnight. The danger is that it remains, but can no longer be trusted. During much of the early Pleistocene, warm and humid conditions support extensive forest environments across the region. Rainfall varies, dry seasons come and go, and plant communities shift. Yet the landscape still provides enough continuity for a Gigantopithecus to move among productive feeding areas. Fruit, leaves, roots, shoots, and other plant resources are distributed across a broad network of valleys, slopes, river margins, and woodland basins. Local shortages occur, but another productive patch may lie within reach. Over time, global climate cycles begin to change. The transition from the early to the middle Pleistocene marks a profound reorganization in Earth's climatic rhythm. Glacial periods become longer and more intense, and the intervals between major environmental shifts stretch across greater spans. Southern China is far from the great ice sheets, but it is not isolated from their influence. Changes in global temperature alter ocean circulation, monsoon strength, rainfall patterns, and the timing of wet and dry seasons. The fossils from Yanli Cave one belong to this broad turning point. Their presence shows that Gigantopithecus survives during a period when climatic instability is already increasing. The species is not immediately defeated by the new conditions. It remains part of the fauna, still feeding, reproducing, and leaving teeth behind in the limestone landscapes of Guangxi. But the ecological foundation beneath it is becoming less stable. A forest can remain green while becoming less useful to a particular animal. Trees may still cover the hills, but the species producing preferred fruits can decline. Fruiting seasons may become shorter or less synchronized. Evergreen forest may give way to a more open mixture of woodland, scrub, and grass. Drought-tolerant plants may spread while moisture-dependent species retreat into sheltered valleys. The total amount of vegetation may remain substantial, yet its nutritional value and spatial arrangement can change dramatically. This distinction is essential because Gigantopithecus was not simply dependent on plants. It was dependent on a particular balance of plants, seasons, and accessible feeding areas. A giant ape can survive a poor month. It can use fallback food when fruit is scarce. It can alter its route when one valley fails. The problem begins when such temporary responses become the normal condition. By around 700,000 to 600,000 years ago, the evidence suggests that seasonality was becoming more pronounced. The environment shifted toward greater variation between productive and unproductive periods. Forest structure changed, and high-quality food became less consistently available. Gigantopithecus responded by broadening or altering its diet, but the foods replacing preferred resources were often more fibrous and less energy-rich. This is where the forest's unreliability enters the body. A fruiting tree provides concentrated calories. Tough stems and bark may require more chewing for less nutritional return. Roots can be valuable, but may be scattered, seasonal, or costly to obtain. Leaves vary widely in digestibility and chemical defenses. An animal may appear to have many food options while still facing a serious energy shortage. The giant ape's powerful dental system allowed it to process these difficult resources, but that ability could not solve the deeper problem of declining quality. Its jaws could crush and grind. Its enamel could resist abrasion. Its digestive system may have handled large quantities of plant matter. Yet there is a limit to how much low-quality food can compensate for the loss of concentrated energy, especially in an animal with an immense body and slow life history. The landscape itself also becomes more fragmented. Open areas expand between forest patches. River systems shift. Drier slopes support different vegetation from humid basins. Suitable feeding grounds remain, but the corridors connecting them weaken. For a smaller and more agile ape, this mosaic may offer alternatives. For Gigantopithecus, the distance between dependable resources becomes increasingly costly. A fragmented forest changes movement in several ways. An animal must travel farther across exposed ground. Shade becomes less continuous, raising heat stress and water needs. Familiar routes may end at open scrub or dry woodland. Productive patches support fewer individuals before being depleted. Populations that once exchanged members across broad areas can become isolated within separate refuges. Isolation carries risks that are difficult to detect in fossils. Small populations are more vulnerable to local drought, disease, reproductive failure, and random losses. They may contain less genetic diversity, though no Gigantopithecus DNA has survived to test this directly. A few unsuccessful breeding seasons can have lasting effects when reproduction is slow. One valley may lose its population while another persists for thousands of years, creating the illusion of stability at the species level even as the overall range contracts. The cave record hints at this contraction. Earlier sites containing Gigantopithecus are more broadly distributed and often associated with rich forest faunas. Later evidence becomes concentrated in a smaller number of areas, particularly within Guangxi. This pattern must be interpreted cautiously because fossil discovery depends on geology, excavation, and preservation. Still, what survives suggests that the species was increasingly restricted to refuges where suitable habitat remained. These refuges may have delayed extinction. Limestone basins can retain moisture, shelter vegetation, and maintain local water sources during regional drying. Valleys protected from the harshest seasonal conditions may continue producing forest foods after surrounding landscapes become less favorable. Gigantopithecus could persist in such places long after disappearing from more exposed areas, but a refuge is not always a solution. It can become a trap. As populations concentrate into shrinking habitat, competition intensifies. More individuals draw from the same fruiting trees and fallback foods. Disease can spread more easily. Movement between refuges becomes dangerous or impossible. A protected valley may sustain a population through several difficult centuries, then fail during an unusually severe sequence of dry seasons. Fire may also have played a growing role. Charcoal in sediments indicates changing burning patterns across the region. Some fires would have been natural, triggered by lightning during dry conditions. Fire can renew certain habitats, open vegetation, and encourage new plant growth, but repeated burning can also prevent forest recovery and favour more open ecosystems. There is no evidence that human-set fire drove the extinction, and natural processes remain sufficient to explain much of the pattern. Even so, increased fire activity would have added another layer of instability to a forest-dependent species. The contrast with ancient orangutans becomes sharper during this phase. Pongo Weidenreichi also experiences the changing climate, altered forests, and greater seasonality. Yet it survives longer and responds more flexibly. Its smaller body requires less total food. Its climbing ability gives access to canopy resources that remain unavailable to a heavy terrestrial ape. It can exploit a broader vertical landscape, moving among branches, understory, and ground-level foods. Gigantopithecus adjusts, but within narrower limits. Its teeth suggest that it does not simply refuse new foods, it uses them. The problem is that those substitutions do not fully compensate for the declining reliability of its preferred habitat. Flexibility exists, but not enough flexibility. No single drought ends the species. No one glacial cycle closes the forest forever. The pressure builds through repetition. A dry season arrives early. Fruit production falls. Individuals travel farther and rely more heavily on fibrous foods. The rains return, but not as strongly. A population recovers slightly, then faces another poor interval before numbers have fully rebuilt. Across human timescales, the forest still appears alive. Across evolutionary timescales, it is becoming a different system. The giant ape continues moving through it, carrying the adaptations of an older world. Its jaws remain powerful, its teeth remain durable, its memory still guides it toward familiar valleys and fruiting trees. But more often, the route ends in a place that produces less than it once did. The forest has not disappeared, it has become uncertain, and uncertainty is slowly becoming the dominant condition of survival. The more uncertain the forest becomes, the more clearly the giant ape's strengths begin to reveal their hidden cost. Gigantopithecus was not poorly adapted to its environment. For most of its history, it was adapted with extraordinary success. Its size, jaws, teeth, and feeding strategy had allowed it to occupy a powerful position in the ecosystems of southern China for well over 1 million years. The trap was not failure. The trap was that the same features that worked so well under stable conditions became difficult to change when stability disappeared. Evolution does not design for every possible future. It favours traits that succeed under the conditions already present. A large body can deter predators, store energy, process large quantities of vegetation, and improve survival through short shortages. Thick enamel can extend the useful life of teeth exposed to abrasive foods. Massive jaws can open feeding opportunities unavailable to smaller primates. Slow growth and long parental investment can produce capable adults in environments where survival is generally high. Each of these traits is valuable, but each also comes with a cost. A giant body requires a giant flow of energy. Even when metabolism becomes relatively more efficient with increasing size, the total amount of food needed remains enormous. The animal must consume enough to maintain muscles, organs, body temperature, movement, immune function, and reproduction. During wet and productive periods, this demand may be easily met. During repeated seasonal shortages, it becomes a liability that cannot be reduced quickly. Gigantopithecus could not simply become smaller when fruiting seasons shortened. Body size changes through many generations, not through individual choice, nor could it rapidly exchange a digestive system shaped around forest plants for one suited to grasslands or open country feeding. Natural selection can alter a lineage, but only if enough individuals survive and reproduce across a long enough period. A species already declining may not have the population size or time required for such transformation. Its teeth reveal a similar constraint. The powerful molars and thick enamel helped process tough fallback foods, but they were part of a feeding system built around repeated heavy chewing. That system may have favored certain jaw mechanics, facial proportions, and food handling behaviors while limiting others. A primate adapted to crushing and grinding large amounts of plant material does not automatically gain access to every possible food source. There is no evidence that Gigantopithecus developed a radically different strategy such as regular meat consumption, tool-assisted foraging, or long-distance migration into open environments. Occasional ingestion of insects, eggs, or small animal matter cannot be ruled out, since living apes sometimes consume foods outside their dominant diet. Yet nothing in the dental record suggests a major shift away from plant dependence. The forest therefore remained both resource and boundary. As long as woodland foods remained available, Gigantopithecus could survive. When these foods became scattered and seasonally unreliable, the ape could broaden its menu only within the limits of what its body already knew how to obtain and process. Slow reproduction deepened the problem. Great apes generally mature late, reproduce infrequently, and invest heavily in each offspring. Gigantopithecus likely followed the same broad pattern, although no direct life history evidence survives. A population built around slow replacement can remain stable for a very long time when adult mortality is low. Once repeated stress begins increasing deaths or reducing successful births, the same strategy delays recovery. A fast-breeding species may rebound after drought or habitat loss within a few seasons. A giant ape cannot, if adults become weakened. Females reproduce less often, or young take longer to reach maturity. The decline may continue even during temporary environmental improvement. The population carries the memory of past hardship in its age structure. This creates a dangerous lag. A forest may recover after several poor years, but the number of breeding adults may already have fallen. Food improves, yet too few individuals remain to rebuild the population quickly. Another dry interval arrives before recovery is complete. Over time, the species becomes increasingly vulnerable to ordinary events that would once have been survivable. Large home ranges may also have become a disadvantage. If an individual needed access to several seasonal feeding areas, fragmentation could sever the route between them. A forest patch might provide fruit during one part of the year, but lack dependable fallback foods later. Another valley might contain those resources, yet open ground, steep karst ridges, or long dry corridors now stand between them. Smaller primates can sometimes cross narrow gaps through branches, use marginal vegetation, or survive on less food while travelling. Gigantopithecus would have faced a higher energetic cost and greater exposure. The landscape did not need to become completely unsuitable. It only needed to make the connections between suitable places too expensive. Its size may also have limited access to vertical refuges. During food shortages, living orangutans can search different levels of the canopy, reaching small fruiting trees, flexible branches, and scattered foods high above the ground. An enormous adult Gigantopithecus could not safely exploit the same fine branch network. The forest may still have contained food, but much of it could have remained physically inaccessible. This is one of the central contradictions of the extinction. The giant ape may have possessed great feeding power while lacking access to enough feeding locations. Its jaws could process hard or fibrous material, yet its body constrained where it could go to find that material. Strength at the mouth could not compensate for limitation in the landscape. Its ecological specialization was therefore not a single narrow preference, such as dependence on one plant. It was a broader package, large size, heavy ground use, high total energy demand, slow reproduction, strong attachment to forest resources, and limited ability to exploit fragmented canopy habitats. Each feature interacted with the others. Scholars still debate exactly how specialized Gigantopithecus was. Its long survival proves that it was capable of enduring considerable environmental variation. It should not be portrayed as an evolutionary dead end waiting for the first climate shift. The new fossils from Yanli Cave 1 reinforce this point. The lineage remained present through the early-middle Pleistocene transition, when global climate cycles were already becoming more severe. It adapted enough to persist for hundreds of thousands of years afterward. The problem was cumulative. Environmental variability continued. Productive foods became less predictable. Forest structure changed. Populations fragmented. Stress increased. Each adaptation bought time without removing the underlying mismatch between the animal's requirements and the changing world. Evolutionary success can create this kind of commitment. A lineage becomes highly effective within a particular ecological system. Its anatomy, behavior, reproduction, and metabolism all reinforce one another. As long as the system continues, the species appears almost unassailable. When the system changes beyond a certain point, every former advantage becomes difficult to abandon because the traits are interconnected. Gigantopithecus could not reduce its size without altering its growth and life history. It could not broaden its movement without changing its limbs and energetic demands. It could not reproduce faster without changing the entire pattern of great ape development. It could not leave the forest without finding foods and climates its body could tolerate. The ape was not trapped in one cave or one valley. It was trapped inside an evolutionary strategy that had worked too well for too long. This does not make extinction inevitable from the moment the species evolved. Had the forest remained more stable, Gigantopithecus might have survived far longer. Had suitable habitats remained connected, populations might have shifted southward or persisted in refuges. Had climate fluctuations unfolded differently, its powerful feeding adaptations may have continued to succeed. But history offered no such guarantee. The environment changed in a direction that rewarded flexibility, mobility, and lower energetic demands. The giant ape carried instead the legacy of abundance. Its decline reveals a principle repeated throughout natural history. Survival does not always belong to the strongest, largest, or most imposing organism. It belongs to the species whose inherited way of life remains compatible with the world that follows. For Gigantopithecus, that compatibility was slowly disappearing. The body that had once embodied success now required more than the forest could reliably provide, and the path back to a different kind of ape was no longer open. The disappearance of Gigantopithecus becomes more revealing when placed beside an animal that shared much of the same world and did not vanish with it. Ancient orangutans lived in the forests of southern China during the same broad climatic transitions. They encountered changing monsoons, increasing seasonality, shifting vegetation, and the gradual fragmentation of woodland habitats. Their survival shows that climate change alone was not an automatic sentence. The decisive difference lay in how each kind of ape could respond when the forest stopped behaving as it once had. The fossil orangutan most often compared with Gigantopithecus is Pongo weidenreichi, a large-bodied relative of living orangutans known from Pleistocene deposits in southern China and mainland Southeast Asia. It was not identical to any modern species, and its precise relationship to living Bornean Sumatran, and Tapanuli orangutans remains part of a complex evolutionary history. Yet its teeth and jaws place it firmly within the orangutan lineage, giving researchers a valuable ecological contrast with the giant ape. Both animals depended heavily on wooded environments. Both consumed plant foods and likely valued fruit when it was available. Both experienced the same regional decline in environmental stability. Their paths separated not because one inhabited the forest and the other did not, but because they used the forest differently. For an orangutan, the forest is not merely an area of ground covered by trees, it is a three-dimensional network of feeding routes. Fruit can be reached in the canopy, leaves in the middle layers, shoots and bark along trunks, and fallen foods below. A smaller-bodied ape can move between these levels and exploit resources distributed across a vertical space that an extremely heavy animal cannot use so easily. This ability becomes especially important when fruiting grows unpredictable. In a highly productive season, several species may feed from the same abundant trees. During scarcity, survival depends on reaching the small and scattered resources that remain. A cluster of fruit at the end of a flexible branch may provide little value to an ape too heavy to approach it. To an orangutan capable of suspending its weight across several supports, it remains available. Living orangutans are remarkable for the variety of postures they use in trees. They climb vertically, hang beneath branches, bridge gaps with long limbs, and distribute their weight among multiple supports. Their movement can appear slow, but it is carefully controlled and highly efficient. Rather than leaping recklessly, a large adult often tests branches and bends vegetation inward to create a route. This style allows access to foods in places where a more rigid or heavier animal would face serious risk. Pongo weidenreichi may not have moved exactly like modern orangutans, but its evolutionary heritage likely preserved some degree of climbing flexibility. Even partial access to the canopy would have expanded its options during environmental stress. Gigantopithecus, especially if adults reach the commonly proposed extreme body masses, would have been excluded from much of that fine branch world. The difference was not simply one of climbing versus walking. Orangutans could also descend to the ground, move between forest patches, and adjust how much time they spent at different levels. This behavioral flexibility matters because fragmented landscapes do not force every animal into one permanent habitat. A species that can alternate between canopy travel, terrestrial movement, and different feeding heights can combine resources that would be insufficient on their own. Dietary flexibility appears equally important. Orangutans are often described as fruit specialists because ripe fruit can dominate their diet when abundant. Yet living populations survive long periods of scarcity by consuming leaves, bark, shoots, seeds, insects, and other fallback foods. The exact menu varies by region, season, and individual knowledge. This does not mean orangutans can eat anything, but they can rearrange their feeding strategy as conditions change. The fossil record suggests that ancient orangutans retained broader dietary options than Gigantopithecus during the later Pleistocene environmental shifts. Their dental evidence shows adaptation without the same degree of increasing stress seen in the giant ape. They also appear to have maintained more stable access to suitable foods as forests became more seasonal. Body size gave them another advantage. Pongo weidenreichi may have been large compared with many living orangutans, but it was still substantially smaller than Gigantopithecus. A smaller body requires fewer total calories. It can survive on a feeding patch that would be exhausted quickly by a much larger animal. It can cross a poor area while carrying a lower energetic burden. It can also use branches and trees unable to support the largest ape. The advantage compounds during scarcity. Suppose a forest patch produces half as much fruit as it once did. The orangutan may compensate by eating more leaves, travelling into the canopy, and reducing unnecessary movement. Gigantopithecus may also switch foods, but its total demand remains much higher. What is an inconvenient shortage for one species can become a demographic crisis for another. Orangutans also possess an unusual capacity to tolerate irregular food intake. Living individuals can experience cycles of abundance and scarcity, building reserves during productive periods and drawing upon them when fruit declines. Gigantopithecus may have done the same to some extent, since large bodies can store considerable energy, but its greater maintenance cost would have consumed those reserves more rapidly if shortages persisted. Knowledge may have helped Pongo survive as much as anatomy did. Orangutans remember the locations of many food trees and the timing of their fruiting. They can alter travel routes according to changing availability and learn through long association with experienced adults. Ancient orangutans almost certainly relied on comparable memory, although cognition cannot be observed directly in fossil teeth. In an unpredictable forest, such knowledge turns scattered resources into a usable map. A tree that produces fruit only once within a long cycle may still be valuable if the animal remembers where it stands. A protected slope may hold leaves during a dry period. A river corridor may connect two feeding areas without requiring a long crossing through open ground. Flexible movement and strong spatial memory reinforce one another. Gigantopithecus likely possessed considerable memory as well. It was a great ape, not an instinct-driven machine. Its long survival indicates that it could learn routes and respond behaviorally to change. The difference may have been that knowledge could no longer overcome its physical constraints. Remembering a fruiting tree is useful only if the animal can reach it without spending more energy than the food provides. Knowing that resources remain high in the canopy offers little advantage if the supporting branches cannot bear the body. Reproductive biology may also have favoured the smaller ape, though both lineages probably reproduce slowly. Orangutans have among the longest intervals between births of any mammal, so they are hardly fast-recovering animals. Their continued existence should not be interpreted as evidence of demographic resilience without limits. They too are deeply vulnerable to habitat loss. Yet even a small difference in survival or reproductive success can become decisive over thousands of years. If Pongo individuals found slightly more food, crossed gaps somewhat more safely, or maintained healthier body condition through each dry period, their populations could remain stable while those of Gigantopithecus declined. Extinction often emerges from modest differences repeated across countless generations. There is a lesser-known complication in this comparison. Ancient orangutans once occupied a far wider range than they do today. Fossil Pongo remains occur across areas of China and mainland Southeast Asia, where no orangutans survive now. Their persistence during the Gigantopithecus crisis did not protect them from every later environmental change. Over time, their northern populations also disappeared, and the surviving lineage retreated toward tropical forests farther south. The comparison is therefore not between a failed giant and an invulnerable survivor. It is between two forest apes losing ground at different speeds. Pongo had more options, but its world was also contracting. Gigantopithecus reached its limit first. Scholars still debate the precise balance of locomotion, diet, body size, and habitat preference behind that difference. No complete skeleton of either Gigantopithecus or Pongo weidenreichi provides a perfect comparison. Environmental conditions also varied between caves and across time. What survives in the record, nevertheless, points consistently toward greater ecological flexibility in the orangutan lineage. The ancient orangutan could move through more of the forest, reach a wider vertical range of foods and sustain itself with lower total energy requirements. Gigantopithecus possessed greater chewing power and a far larger body, but those strengths operated within a narrower set of possibilities. As the forest became divided, the orangutan could still search among the branches. As fruit became unpredictable, it could combine smaller resources scattered across different levels. As dry seasons lengthened, it endured with less food and more behavioral choice. The giant ape remained formidable, but survival was no longer a contest of force, it was a contest of options, and the smaller ape had more of them. The advantage held by the smaller ape does not mean that one pressure alone explains the disappearance of the larger one. Extinction usually emerges from several forces acting together, and the farther the evidence lies in the past, the more carefully those forces must be separated from speculation. Climate change, food competition, predators, disease, population isolation, and human presence have all been proposed as possible parts of the story. Some are strongly supported, others remain plausible but unproven. No single explanation fully accounts for every detail. The clearest evidence points toward environmental change. By the later Middle Pleistocene, southern China had become more seasonal, forests were less stable, and high-quality foods were increasingly difficult to obtain. Gigantopithecus teeth show greater dietary stress and a heavier reliance on fallback resources. Cave sediments and pollen reveal changing vegetation. Dating places the species' final disappearance between roughly 295,000 and 215,000 years ago, after a long period of mounting ecological pressure. This does not mean climate itself directly killed the last individuals. Climate acts through the landscape. It changes rainfall, plant growth, water availability, fire frequency, and the distribution of animals competing for the same resources. The giant ape was not struck down by colder air or one catastrophic drought. Its habitat became less capable of supporting the energetic and reproductive demands of its lineage. Competition may have intensified as suitable forest contracted. Gigantopithecus shared its environment with ancient orangutans, monkeys, pigs, deer, tapirs, elephants, and other plant-eating mammals. These animals did not all consume identical foods, but their diets overlapped. During seasons of abundance, overlap may have mattered little. When fruiting declined and fallback foods became more important, the same forest patch had to support more mouths drawing from fewer dependable resources. Competition does not require violent encounters. It often occurs invisibly. A troop of monkeys feeding in a fruiting tree reduces what falls to the ground. Pigs reaching a patch first consume roots and fallen fruit before a slower animal arrives. Elephants break branches and open vegetation, sometimes creating feeding opportunities but also removing large quantities of plant material. Ancient orangutans exploit canopy foods inaccessible to a heavy terrestrial ape, yet they may still compete for fruit once it falls. Gigantopithecus may have been physically capable of displacing many smaller animals from a local feeding site. Size can provide dominance at close range, but dominance is useful only when food is concentrated enough to defend. Scattered resources cannot be controlled efficiently. A giant ape cannot guard every fruiting tree across a fragmented landscape, nor can it prevent birds, monkeys, pigs, and other animals from feeding before it arrives. The decline of population density may have made competition more damaging. When individuals must travel farther between patches, they spend more energy and arrive later. When several species converge on the same refuge during dry periods, the most adaptable feeders gain an advantage. Gigantopithecus could process tough foods, but other animals may have reached them more quickly, used more diverse alternatives, or survived on smaller amounts. Predation is another possibility, though the evidence is limited. Healthy adult Gigantopithecus individuals were probably too large to be routine prey for most carnivores. Large cats, hyenas, and other predators inhabited Pleistocene southern China, and exceptionally powerful predators may have posed a risk under certain conditions. Yet there are no widely accepted fossil assemblages showing repeated attacks on the giant ape. Predators could still have affected vulnerable individuals or small populations indirectly. An injured, sick, or nutritionally weakened animal would be easier to attack. Isolated populations could be harmed by the loss of even a few breeding adults. Carnivores might also compete for sheltered routes or water sources, increasing the cost of movement during difficult seasons. These effects are possible, but they cannot currently be measured from the fossil record. Disease leaves even fewer traces. Habitat fragmentation can concentrate animals around limited water and food, creating conditions in which pathogens spread more easily. Nutritional stress weakens immune defenses. Small populations may become more vulnerable to outbreaks or reproductive problems. Yet no preserved tissue, ancient DNA, or diagnostic bone lesions demonstrate a disease-driven extinction. Disease may have contributed, but it remains beyond direct confirmation. The role of humans attracts more attention because it offers a dramatic narrative. Early members of the human lineage were present in Asia during portions of the long existence of Gigantopithecus. Stone tools and hominin fossils show that human relatives occupied varied environments across the continent. It is therefore possible that humans and giant apes sometimes lived within the same broad regions. Possibility, however, is not evidence of direct contact. No secure archaeological site shows Gigantopithecus remains with cut marks, butchery damage, embedded weapons, or clear association with human hunting activity. No known accumulation demonstrates that people regularly killed or consumed the animal. The idea that human hunters exterminated the largest ape is popular because it resembles later stories of megafaunal loss. But the current fossil record does not support presenting it as the main cause. Human competition for plant foods is also difficult to establish. Early hominins could exploit roots, fruits, nuts, small animals, and many other resources, but their population density was probably low across much of the region. Their tool use, mobility, and dietary flexibility may have allowed them to enter habitats unavailable to Gigantopithecus. Yet there is no direct evidence that they removed enough food to drive the ape into decline. Fire is sometimes included in this debate. Humans were capable of using fire in parts of the Pleistocene world, although the timing and regularity of controlled fire use in southern China remain complex questions. Charcoal in cave sediments does not automatically indicate human burning. Lightning and natural dry season fires can produce the same material, even where humans were present. Distinguishing deliberate landscape burning from natural fire is extremely difficult. It is possible that human activity added local pressure to populations already weakened by climate change. Occasional hunting, disturbance, competition around water, or burning could matter more when only a few isolated groups remained. But this is a layered possibility, not a demonstrated event. The extinction pattern does not require human intervention to make sense. Environmental instability, dietary stress, fragmentation, and slow reproduction already provide a strong explanation. Another popular idea claims that Gigantopithecus survived much later in remote mountains and inspired stories of wild giants. Such claims connect the ape to Bigfoot, the Yeti, or regional traditions of hairy forest beings. There is no credible fossil, genetic, photographic, or ecological evidence for survival into recent times. The youngest securely dated remains belong hundreds of thousands of years in the past. Legends may reflect many sources, including encounters with living bears, orangutans, unfamiliar people, or symbolic storytelling. Linking them directly to Gigantopithecus requires evidence that does not exist. The scientific explanation is less theatrical but more revealing. The giant ape did not need a singular enemy. It faced a network of pressures that reinforced one another. Climate-altered vegetation, reduced food increased competition, poor nutrition lowered resilience, fragmentation isolated populations, slow reproduction delayed recovery, predators, disease, and perhaps occasional human disturbance may have added local losses. Extinction can emerge from this accumulation without leaving one decisive mark. A species may disappear because every remaining population becomes slightly less secure at the same time. One refuge dries, another loses key fruiting trees, a third becomes too isolated for individuals to find mates. No single event seems sufficient, but together they close every route of escape. What survives in the record strongly supports climate-driven ecological change as the central force. Competition and demographic weakness likely deepened its effects. Human involvement remains possible only in a limited and unconfirmed sense. Predation and disease cannot be ruled out, but neither can they be demonstrated. The mystery is therefore not solved by choosing one villain. It is solved by recognizing how a powerful species can become vulnerable when several ordinary pressures converge. Gigantopithecus did not need to lose one final battle. It only needed to run out of places where its old way of life still worked. By the time Gigantopithecus enters the final portion of its history, the decline is no longer theoretical. The changing forest has already left marks in its teeth. Suitable habitats are more fragmented. High-quality foods are less dependable. Populations that once occupied a broad network of valleys, wooded basins, and river corridors now appear to be contracting into fewer refuges. The species is still present, but the conditions supporting it are thinner, more uneven, and increasingly temporary. The best current evidence places its disappearance within a window between roughly 295,000 and 215,000 years ago. This is not the date of one final death. It is the interval during which Gigantopithecus vanishes from the known fossil record across the studied caves of southern China. The precision comes from combining multiple dating methods across many sites, rather than relying on a single tooth or sediment layer. Even so, the evidence remains incomplete. The last fossil found is not necessarily the last individual that lived. Small populations may have persisted beyond the youngest known remains in places that have not been preserved, excavated, or recognized. What the record can show is that by this late stage, Gigantopithecus was no longer living under the relatively favorable conditions that had supported earlier populations. The climate had become more variable, forest structure had changed, seasonal shortages were stronger. The ape's diet had become less stable, and its teeth suggest greater dependence on fallback foods. Its surviving populations were likely experiencing a form of ecological compression, more individuals, or at least more competing species, drawing from fewer dependable patches. A refuge can sustain a declining species for a surprisingly long time. Sheltered limestone valleys may retain moisture when exposed slopes dry. Deep soils near rivers can support vegetation after surrounding woodland opens. Caves and karst systems can preserve springs and cool microclimates. Such places may have allowed isolated groups of Gigantopithecus to endure long after the broader landscape became unfavorable. But refuge populations face problems of their own. Their habitat is limited. A productive valley can support only so many giant apes once its fruiting trees, roots, shoots, and fallback foods are heavily used. Individuals must either travel farther or accept poorer nutrition. If surrounding corridors have become too open, dry, or fragmented, movement to another refuge may carry a high energetic cost. The final populations were probably not arranged in one continuous range. They may have existed as scattered groups separated by stretches of unsuitable habitat. Some could still exchange individuals during favourable periods. Others may have become effectively isolated. No genetic material survives to reveal how connected they were, but population fragmentation is a reasonable inference from the shrinking distribution and changing environment. Isolation weakens resilience in several ways. A local population cannot easily be replenished after drought, disease, or reproductive failure. Individuals may have greater difficulty finding mates. Genetic diversity can decline, making populations more vulnerable to environmental stress. Though this cannot be tested directly in Gigantopithecus, a single poor sequence of seasons can eliminate a group that would once have been supported by immigration from a neighbouring valley. Slow reproduction magnifies every loss. If Gigantopithecus followed the general great ape pattern, females likely produced relatively few offspring over a lifetime, with long intervals of care and development. A decline of only a few breeding adults can therefore alter the future of an entire population. An animal may still be visible in the landscape for generations, while births quietly fail to replace deaths. The teeth from later deposits reflect this pressure. Microwear indicates increased use of tougher, more fibrous foods. Trace element patterns suggest greater nutritional variability and physiological stress. These signs do not mean that every late individual was starving. Some may have remained healthy in local pockets of abundance. The broader pattern, however, suggests that the average ecological conditions had worsened. A giant ape can survive on fallback foods for a time, but survival is not the same as successful reproduction. Low-quality diets may maintain an adult through a dry season while reducing fertility, slowing growth, or increasing vulnerability to illness. The population can therefore decline without leaving dramatic evidence of mass death. There may be no bone bed, no catastrophic layer, and no final congregation of dying animals, only fewer individuals returning to the same feeding grounds. The fossil record itself becomes quieter. Teeth remain the most likely parts to survive, yet later remains are less common. This could reflect fewer animals, reduced range, poorer preservation, or some combination of all three. Researchers must avoid treating absence as absolute proof, but when the declining fossil signal aligns with environmental and dietary evidence, it becomes part of a coherent pattern. The last populations may have responded with greater movement. Familiar valleys no longer provided enough food throughout the year, forcing individuals to travel between seasonal resources. A route that once connected forest patches may now cross open woodland or scrub. Heat exposure increases. Water becomes less reliable. The animal must spend more energy reaching food that itself provides less energy. This is where body size becomes especially unforgiving. A smaller primate can sometimes survive by reducing intake, resting more, or exploiting scattered resources. Gigantopithecus still needs to maintain an immense frame. It cannot shrink its daily requirements simply because the forest has changed. Each journey must be repaid through feeding, and late Pleistocene landscapes were offering fewer opportunities for that repayment. Ancient orangutans may have continued moving through canopy fragments and using smaller patches that could not support Gigantopithecus. Pigs and monkeys could exploit scattered foods quickly. Deer and bovids could shift into more open habitats. early humans were present, carried flexible diets and tool-assisted behavior. The giant ape remained tied to a narrower ecological path. There may have been moments of partial recovery. Wetter decades could restore fruiting, forest patches could expand, a local population might grow slightly after several favourable generations. Such improvement would explain how the species persisted through long environmental instability rather than disappearing immediately. But temporary recovery does not remove the underlying vulnerability. Another dry cycle follows. A river changes course. Fire opens a wooded slope. Key trees fail to regenerate. The distance between refuges widens. Each event removes part of the margin that allowed the population to survive the previous one. The final extinction may therefore have unfolded unevenly across southern China. One population disappears centuries or millennia before another. A sheltered basin in Guangxi continues to support the ape, while populations farther away have already vanished. The last survivors may not represent the healthiest or largest group, only those fortunate enough to occupy the final suitable habitat. No fossil can identify that last refuge with certainty. The known cave sequence provides a regional extinction window, not a final address. The true last population may have lived beyond the area sampled by the 22 caves. It may have survived for a time in a valley whose sediments were later eroded or whose fossils remain undiscovered. The evidence narrows the ending but does not reveal its final scene. That scene was probably quiet. There is no reason to imagine a last giant ape understanding that its species was ending. It would have followed familiar routes, searched for fruit, stripped fibrous plants, rested in shade, and responded to the next dry season as generations before it had done. Its world would still contain trees, rivers, other apes, elephants, pigs, deer, and predators. Nothing in the landscape would announce that one evolutionary lineage had reached its final generation. The last individual may have died from age, disease, injury, or ordinary nutritional stress. Its teeth may never have entered a cave. Its bones may have dissolved beneath humid soil. Scavengers may have scattered the remains. The species could end without leaving a final fossil. This is one of the most unsettling features of extinction. A lineage that survives for more than 1 million years can disappear without a visible boundary. The forest continues. Other animals adapt. Seasons return. Only one immense form no longer moves beneath the canopy. By roughly 215,000 years ago, the known record has fallen silent. Gigantopithecus is gone from the caves that preserved its history. The ecological system has crossed a threshold beyond which its combination of size, diet, movement, and slow reproduction can no longer be sustained. The giant did not vanish because it lacked strength. It vanished because strength could not solve the final problem, a world in which every remaining path demanded more energy than it gave back. An animal known almost entirely from teeth leaves room for science, but it also leaves room for fantasy. Gigantopithecus is large enough to inspire awe, incomplete enough to invite reconstruction, and distant enough that almost any image can seem possible to an audience unfamiliar with the limits of the evidence. The missing skull, limbs, hands, feet, and spine do not merely create uncertainty. They create an empty body that popular culture has repeatedly filled with monsters, giants, and supposed survivors. The process begins with scale. A molar far larger than that of a living human or orangutan naturally suggests an enormous owner. Early researchers had few fossils with which to test their estimates, and the public imagination moved more quickly than comparative anatomy. Gigantopithecus was described in illustrations as a creature capable of standing 3 meters tall. sometimes even more, with the shoulders of a gorilla and the posture of a human. These images were memorable, but they often transformed uncertain estimates into apparent facts. There is no confirmed fossil showing how tall the animal stood. There is no pelvis proving habitual bipedalism, no femur revealing leg proportions, and no spine showing how the torso was balanced. A very large ape could rear upright, as living apes do, without regularly walking on two legs. Yet once an artist presents an upright giant, the image begins to repeat itself. Later illustrations copy earlier ones, documentaries borrow familiar silhouettes, and speculation gradually acquires the visual authority of evidence. The same happens with weight. Estimates approaching 300 kilograms are plausible, but not directly measured. Some individuals may have been smaller, and males and females may have differed greatly in size. The true body could have been more compact, more elongated, or differently proportioned from the common reconstruction. Tooth size provides a foundation for estimating mass, but it does not permit the precision sometimes claimed in popular accounts. Color is even less certain. Gigantopithecus is often shown with reddish hair because its closest living relatives are orangutans. This is a reasonable artistic choice, but not a fossil fact. It may have been dark brown, black, reddish, or patterned in ways that left no trace in enamel. Hair length, facial skin, cheek structure, and expressions are equally unknown. Every reconstruction must invent them. These necessary inventions are not inherently misleading. Paleontological art must turn fragments into visible organisms. The problem arises when the boundary between evidence and interpretation disappears. A museum model or cinematic image can become so persuasive that viewers assume a complete skeleton exists somewhere behind it. In reality, the artist is often working from a few jaws, many teeth, distant evolutionary relationships, and informed guesswork. The lack of a body also allowed Gigantopithecus to become entangled with legends of living wild giants, Bigfoot enthusiasts, Yeti believers, and writers interested in unknown primates have long proposed that the species survived into the recent past, or even remains alive in remote forests. The suggestion has an immediate appeal. Here is a real giant ape from Asia, known from incomplete fossils, inhabiting landscapes associated with stories of mysterious hairy beings. The leap from extinct pongene to hidden survivor can feel small when presented without chronology. In reality, it is enormous. The youngest securely dated Gigantopithecus remains are more than 200,000 years old. No credible fossils place the species near the end of the last ice age, much less within historical times. No preserved hair, scat, bone, DNA, photograph, or reliably documented observation supports its survival. A breeding population of animals weighing hundreds of kilograms would require vast quantities of food and leave abundant ecological traces. It would create feeding damage, trails, nests, carcasses, droppings, and genetic material. Remote forests can conceal rare species, but they do not suspend the basic requirements of population biology. The environments themselves have also changed profoundly. Gigantopithecus belonged to Pleistocene ecosystems that no longer exist in the same form. The forests of southern China have shifted, fragmented, and been transformed repeatedly by climate and later human land use. A species already unable to survive environmental changes hundreds of thousands of years ago is unlikely to have passed invisibly through every later climatic and ecological upheaval. Attempts to connect it to the Yeti create additional problems of geography and habitat. Gigantopithecus fossils come primarily from warm and subtropical parts of southern China and neighbouring regions. The classic Yeti tradition is associated with high Himalayan environments of snow, rock, and alpine conditions. No evidence shows that the giant ape possessed adaptations for such cold, high-altitude landscapes. Moving it from humid southern forests to Himalayan ice requires an evolutionary and geographic journey unsupported by fossils. Bigfoot associations are even more distant. No confirmed Gigantopithecus fossils have been found in the Americas. To place the animal there would require a population to cross northern Asia, enter Beringia, survive severe cold, move into North America, and leave no recognized fossil trail across that immense route. The hypothesis adds migration, adaptation, and recent survival without supplying evidence for any of them. Stories of wild people and forest beings remain culturally important, but they should not be treated as straightforward zoological reports. Such traditions can emerge from encounters with bears, monkeys, unfamiliar human groups, footprints distorted by snow, or symbolic ideas about wilderness and the boundary between human and animal. They may preserve memories of real experiences, but linking them to one fossil ape requires more than resemblance. Gigantopithecus has also been drawn into claims about ancient giants, lost civilizations, and hidden human ancestry. Its name encourages confusion because giant ape can easily become giant man in retelling. Yet the protein evidence is clear it belongs to the orangutan branch of the great ape family. It is not a known human ancestor, not a giant hominin, and not evidence for races of enormous prehistoric people. The confusion is partly historical. When Gigantopithecus was first described, the structure of ape and human evolution was far less clear. Some researchers genuinely considered whether it might occupy a position near the human lineage. Those proposals belong to a period when the fossil record was sparse, and molecular evidence did not exist. Science moved forward as better comparative material and ancient proteins became available. Popular culture, however, often preserves discarded possibilities long after research has left them behind. Another misconception portrays Gigantopithecus as a failed brute, too large and unintelligent to survive against cleverer humans. This story is dramatic but unsupported. There is no direct evidence that people hunted it into extinction, and no fossil brain case survives from which to estimate its brain size. As a great ape, it was likely capable of substantial learning, memory, and social awareness. Its extinction reflects ecological mismatch, not a moral contest between strength and intelligence. The opposite exaggeration is equally misleading. Some accounts imagine the animal as nearly invincible, the undisputed ruler of the forest. Great size would have protected healthy adults from many predators, but it also imposed high food demands and slow reproductive recovery. Gigantopithecus was neither helpless nor unstoppable. It was a real animal living within ecological limits. Its nickname as the King of Apes captures its scale but can obscure the quiet reality of its life. It probably spent far more time chewing, resting, travelling between feeding grounds, and responding to seasonal shortages than fighting dramatic battles. Fossil animals are often remembered through their most spectacular trait. For Gigantopithecus, that trait is size. Yet the extinction story shows that the less visible traits mattered more: diet, mobility, reproductive pace, habitat dependence, and the capacity to adjust. The missing bones will continue to invite speculation because there are questions science cannot yet answer. A future discovery could transform the reconstruction. One limb bone might clarify locomotion. A partial skull could reveal facial proportions and brain case size. A skeleton associated with well-dated sediments could force major revisions to current estimates. The evidence remains incomplete, and responsible reconstruction must remain open to change. But openness is not the same as accepting every claim. Scientific uncertainty has boundaries. Researchers may debate whether the animal weighed 200 or 300 kilograms, how often it climbed, or which fallback foods mattered most. That uncertainty does not support recent survival, human ancestry, or identification with legendary creatures. The strongest mystery is already present in the evidence. There is no need to turn Gigantopithecus into a monster. A real ape evolved to a scale unmatched by any living primate, survived across immense climatic changes, and disappeared when the balance between its body and its environment finally broke. Its teeth were sold as dragon bones before science recognized them. Its lineage was identified through proteins preserved for nearly 2 million years. Its extinction was reconstructed from cave sediments, pollen, wear marks, and chemistry almost invisible to the human eye. The missing skeleton makes the giant difficult to see, but it should not make it whatever imagination wishes. The empty spaces around the fossils are part of the story. They remind us that the past is not recovered whole, and that mystery becomes most powerful when the limits of knowledge remain visible. What Gigantopithecus leaves behind is not a complete body, but a warning written in fragments. Its teeth reveal a species that was neither primitive nor poorly adapted. It was the product of a successful evolutionary lineage, one that had survived for more than 1 million years across the shifting forests of southern Asia. Its disappearance did not erase that success. It exposed the conditions on which that success had always depended. The ancient proteins preserved in its enamel place it firmly within the pongin branch of the great ape family, closer to orangutans than to humans, chimpanzees, or gorillas. This relationship gives the giant ape a living point of comparison, but it also reveals how much evolutionary history has been lost. Gigantopithecus was not simply an oversized orangutan. It belonged to a separate lineage that diverged millions of years earlier and developed its own anatomy, ecology, and response to the Pleistocene world. The orangutan branch was once far more diverse and widespread than it is today. Fossil pongines occupied parts of Asia where no wild orangutans now survive. Gigantopithecus represents one of the most extreme experiments within that broader history, a great ape evolving enormous jaws, exceptionally thick enamel, and a body large enough to occupy a ground-based feeding niche unlike that of any living primate. Its existence widens the image of what an ape can be. Modern species provide only a small sample of the forms evolution has produced. Chimpanzees, bonobos, gorillas, and orangutans are not the final or inevitable designs of great ape evolution. They are the surviving branches of a tree once crowded with other possibilities. Some were smaller, some moved differently, some occupied environments that no longer exist. One became a giant beneath the forests of southern China. The loss of Gigantopithecus therefore represents more than the disappearance of a single unusual species. It removes an entire way of being an ape. No living primate now combines such immense size with the dental adaptations preserved in its jaws. No animal fills exactly the same ecological role. Once the lineage ended, its evolutionary knowledge, the inherited solution developed across millions of years, ended with it. That knowledge had been effective for an extraordinary span. Gigantopithecus persisted through repeated climatic cycles, changing monsoons, altered animal communities, and shifts in forest structure. The fossils from Yanli Cave reinforced this endurance. During the early Middle Pleistocene transition, when global climate rhythms were becoming longer and more intense, the species remained present. It was not fragile in the ordinary sense. It could withstand change. but not unlimited change. This distinction matters when extinction is described as failure. Species do not fail because they vanish, just as survivors do not prove themselves superior in every respect. Evolution has no permanent winners. A lineage succeeds only while its traits remain compatible with the environments that follow. Gigantopithecus was compatible with its world for longer than Homo sapiens has yet existed. Its final vulnerability emerged from the interaction of many traits that had once served it well. Large size reduced threats from predators and may have improved feeding efficiency, but it also raised total energy requirements. Strong jaws and durable molars expanded access to difficult plant foods, but those foods could not always replace the calories lost when fruit declined. Ground-oriented movement opened resources below the canopy, but restricted access to food scattered across smaller branches. Slow reproduction supported long development and parental investment, but prevented rapid recovery when populations fell. None of these features was fatal on its own. Together, under increasingly seasonal and fragmented conditions, they formed a narrowing corridor. The ape could alter its diet, but not enough. It could move between feeding grounds, but at rising cost. It could survive poor seasons, but not rebuild quickly before the next one arrived. This is the deeper lesson of specialization. Specialization is often described as weakness, but it can be a source of remarkable success. A species becomes exceptionally good at using a particular environment or resource. It reduces competition, develops powerful anatomical solutions, and occupies a niche others cannot. The danger appears only when that niche changes faster than the lineage can follow. Gigantopithecus was not too specialized to survive every disturbance. It survived countless disturbances. Its extinction came when change became persistent enough to transform the basic structure of its habitat. Forest remained on the landscape, but the pattern of food, season, and accessibility no longer matched the demands of the giant body. The same process continues around living species today. Orangutans survived the climatic crisis that eliminated Gigantopithecus, but their survival was not permanent security. Modern orangutans now occupy a fraction of their former range and face severe pressure from habitat loss, fragmentation, fire, and human activity. Their flexibility has limits. The comparison is sobering because the traits that once helped Pongo outlast the giant ape cannot guarantee survival in landscapes altered at unprecedented speed. Gigantopithecus also reminds us that the most important stages of extinction can occur before the final disappearance. The species was already in danger when populations became isolated, diets worsened, and physiological stress increased. By the time the last individuals remained, much of the extinction had effectively happened. The final death was only the closing point of a decline that had unfolded across thousands of generations. This makes the fossil record especially difficult to read. Teeth appear, become less common, and stop. The silence afterwards seems sudden, but the biological process was probably long and uneven. Some populations vanished while others remained in refuges. A wetter period may have delayed the end. A protected valley may have supported one final group. The true last survivors may never be found. Future discoveries could still alter parts of this story. Another cave may extend the known range. A securely dated tooth may shift the extinction window. A limb bone could transform understanding of locomotion. A skull might revise body size estimates and reveal unexpected facial anatomy. New methods may recover additional proteins or environmental molecules from sediments. The picture is clearer than it was when the first tooth appeared in a Hong Kong pharmacy, but it is not finished. The 13 teeth from Yanli Cave 1 show how even a modest discovery can change the shape of the history They do not provide the missing skeleton, yet they occupy an important interval and show the species surviving through a major climatic transition. They connect the prosperous early populations with the later ape under increasing environmental strain. The gap grows smaller, one tooth at a time. That is how Gigantopithecus has returned to view not through one spectacular skeleton, but through accumulation. A tooth sold as dragon bone, a lower jaw recovered from a cave, pollen grains preserved in sediment, microscopic scratches across enamel, chemical elements deposited while an animal was growing, proteins surviving where DNA could not. Each fragment alone is limited. Together, they reveal a lineage that lived, adapted, struggled, and disappeared. The animal itself remains beyond complete recovery. No reconstruction can show with certainty how its shoulders moved, how its calls sounded through the forest, or what expression crossed its face when rain returned after a long dry season. Science can estimate its body and follow the decline of its habitat, but much of its lived existence has passed outside memory. Perhaps that is why the surviving teeth carry such weight. They are small compared with the animal that produced them, but they have outlasted every forest it knew. The trees fell and returned in different forms. Rivers shifted, caves filled with sediment. Other animals moved south or vanished. Human populations spread across landscapes where the giant ape had once searched for food. Through all of this, enamel remained in darkness beneath limestone. Now the pace of the story slows, as every extinction story eventually must. The forest no longer holds the body of Gigantopithecus. No heavy movement passes beneath the canopy. No immense jaw closes over fallen fruit or fibrous stems. The paths it followed have been covered by later soils, cut by water, or erased by generations of vegetation. Even the climate that shaped its final centuries has moved on. Yet the absence is not empty. In museum drawers and laboratory trays, the teeth remain. Their surfaces carry scratches made during meals consumed hundreds of thousands of years ago. Their chemistry holds traces of rain, roots, leaves, and seasons that no human ever witnessed. They preserve a world not as a picture, but as pressure and mineral, growth and wear. Time usually removes living things without explanation. Flesh disappears first, bone follows. Landscapes change until the original setting becomes almost impossible to imagine. What survives is accidental, a protected cave, a resistant tooth, a layer of sediment left undisturbed. From those accidents, a story returns. It is the story of a giant that was not defeated in battle, but slowly separated from the conditions that had made its life possible. It is the story of forests that remained green while becoming unfamiliar, of strength that could not substitute for flexibility, and of an evolutionary lineage reaching the edge of what it could endure. Long after the last Gigantopithecus vanished, orangutans continued through the branches, humans spread farther across Asia, and the limestone hills remained above the rivers. Nothing paused to mark the loss. Only much later did a single oversized molar emerge from a collection of dragon bones and open a path backward through time. At the end of that path stands no complete skeleton, only the outline of an immense ape fading among trees. The image is uncertain, softened by distance, but it lingers a quiet giant beneath a changing canopy, carrying the weight of an older world until the forest could carry it no longer.